Level 1. Gravity. Gravity is the invisible force that holds the universe together. It is the reason why objects fall, why planets orbit stars, and why we stay grounded on Earth. At its core, gravity is the attraction between any two objects with mass. The more massive an object, the stronger its gravitational pull. On Earth, gravity gives objects weight and causes them to accelerate toward the ground at 9.8 meters per second squared. If you drop a ball, gravity pulls it downward, making it speed up as it falls. This force acts on everything, from a feather drifting through the air to a meteor hurtling through space. Gravity isn't just limited to Earth, it governs the motion of celestial bodies. The moon stays in orbit around Earth, and Earth orbits the sun due to gravity. The same force that keeps your feet on the ground is responsible for shaping galaxies and bending light around massive objects in space. Unlike forces like magnetism, gravity works universally, affecting everything, no matter the material. Even though it's one of the weakest fundamental forces, it has an infinite range and plays a crucial role in the structure of the cosmos. Without gravity, everything would drift aimlessly, and the universe as we know it wouldn't exist. Level 2. Matter. Matter is the foundation of everything in the universe. It is anything that has mass and takes up space. From the tiniest grain of sand to the largest galaxy, all physical substances are forms of matter. It is what makes up the earth, the air we breathe, the water we drink, and even our own bodies. At its most basic level, all matter is made up of atoms, which are the building blocks of everything around us. Atoms themselves are composed of protons, neutrons, and electrons, which determine the characteristics of different substances. The way atoms combine forms the vast variety of materials we encounter, from simple elements like oxygen and gold to complex compounds like proteins and plastics. Matter is not limited to what we can see. Scientists have discovered that much of the universe is composed of dark matter, an invisible substance that doesn't interact with light, but exerts gravitational effects on galaxies. Understanding matter allows us to explore everything from the chemical reactions that fuel life to the forces shaping the cosmos. Level 3. States of matter. Matter can exist in different states or phases depending on temperature and pressure. The four fundamental states of matter, solid, liquid, gas, and plasma, each have unique properties that determine how substances behave. Solids have a fixed shape and volume because their atoms or molecules are tightly packed together. Materials like metal, ice, and wood maintain their form unless acted upon by an external force. In contrast, liquids have a definite volume but no fixed shape, flowing freely to take the shape of their container. Water, oil, and mercury are examples of liquids, where particles move more freely than in a solid, but still remain connected. Gases have neither a fixed shape nor a fixed volume. Their particles move rapidly and spread out to fill any space available, as seen in air, steam, or helium. The fourth state, plasma, occurs at extremely high temperatures when atoms lose their electrons, creating a charged state of matter. Plasma is found in stars, lightning, and neon lights. Level 4. The scientific method. This is the systematic process scientists use to explore questions, test ideas, and uncover truths about the natural world. It is the foundation of all scientific discovery, ensuring that conclusions are based on evidence, logic, and repeatable experiments rather than opinion or speculation. The process begins with observation, where scientists notice a pattern, phenomenon, or problem. This leads to a question such as, why do plants grow faster in sunlight? From there, they form a hypothesis, a testable statement predicting an outcome. For example, if a plant receives more sunlight, then it will grow taller. Next comes experimentation, where controlled tests are conducted to gather data. A good experiment includes variables: the independent variable, which is what is changed, the dependent variable, which is what is measured, and controlled variables, which are factors that are kept constant. After collecting data, scientists analyze the results to determine whether they support or contradict the hypothesis. If the hypothesis is confirmed, it may contribute to a broader scientific theory. If the results do not support it, the hypothesis is revised or discarded, and the process repeats. The final step is communication, where scientists share their findings through research papers, presentations, or peer-reviewed journals to allow others to verify or challenge their conclusions. The scientific method is more than just a checklist. It is a continuous cycle of questioning, testing, and refining knowledge. It has led to groundbreaking discoveries, from understanding gravity to developing modern medicine. Level 5. Density. Density is the measure of how much mass is packed into a given volume. It explains why some objects float while others sink, and why different materials feel heavier or lighter, even if they are the same size. The formula for density is simple: mass divided by volume. This means that an object with a lot of mass in a small space has high density, while an object with less mass in the same space has low density. In everyday life, density is easy to observe. A brick and a sponge may be similar in size, but the brick is much heavier because it has more mass packed into the same volume, making it denser. Water has a density of 1 gram per cubic centimeter. Objects with a density greater than this, like a rock or metal, will sink in water, while those with lower density, like wood or ice, will float. This is why ships, even though they are made of heavy metal, can float. They are designed with hollow spaces to reduce their overall density. Density is a key factor in science and nature. The Earth's core is made of denser metals like iron and nickel, while the atmosphere consists of low-density gases like nitrogen and oxygen. Hot air balloons rise because heated air has lower density than the cooler surrounding air. In space, white dwarf stars are incredibly dense, packing a sun's worth of mass into a space the size of Earth. Understanding density helps explain how substances interact and why objects behave differently in various environments. It is a fundamental concept in physics, engineering, and even natural phenomena, shaping the way the world around us works. Level 6. Energy. Energy is the ability to do work or cause change. It exists everywhere, from the heat of the sun to the movement of your body. Energy cannot be created or destroyed, only transferred or transformed, a principle known as the law of conservation of energy. There are many forms of energy. Kinetic energy is the energy of motion, found in moving cars, flowing water, or a thrown baseball. Potential energy is stored energy, waiting to be released, like a stretched rubber band or a rock sitting on a cliff. Other forms include thermal energy, which comes from heat, chemical energy, stored in food and fuel, and electrical energy, which powers our homes. Even light and sound carry energy in different ways. Energy constantly moves and changes forms. When you eat food, your body converts chemical energy into kinetic energy for movement and thermal energy to keep you warm. A falling object transforms potential energy into kinetic energy as it speeds toward the ground. Plants capture sunlight and convert it into chemical energy through photosynthesis, fueling life on Earth. Every process in the universe depends on energy. From the fusion reactions in stars to the electricity that powers our world, energy is the driving force behind all motion, growth, and change. Understanding energy is key to everything from physics and engineering to biology and space exploration. Level 7. Force. The invisible push or pull that makes objects move, stop, or change direction. It is the reason why a ball rolls when kicked, why a car slows down when you hit the brakes, and why the Earth orbits the Sun. In physics, force is measured in newtons and is defined as mass times acceleration. Forces come in many forms. Gravity pulls objects toward the ground, keeping us anchored to Earth. Friction resists motion, like when you slide a book across a table and it eventually stops. Applied force happens when you physically push or pull an object. Tension forces keep ropes and cables tight, while normal force prevents objects from falling through solid surfaces. Even the air around us exerts air resistance, slowing down falling objects. Forces can be balanced or unbalanced. When forces are balanced, an object remains still or moves at a constant speed, like a book resting on a table. But when forces are unbalanced, motion occurs. A stronger force in one direction will cause an object to accelerate, slow down, or change direction. This is how engines propel rockets, how magnets attract or repel, and how waves push against the shore. Every interaction we experience involves force. Whether lifting a cup, driving a car, or feeling the pull of gravity, forces shape the way the universe moves and behaves. Understanding force helps explain motion, engineering, and even the fundamental forces of the universe. Level 8. Acceleration. Acceleration is the rate at which an object's velocity changes over time. It describes how quickly something speeds up, slows down, or changes direction. Unlike speed, which only tells us how fast something moves, acceleration tells us how motion is changing. It is measured in meters per second squared and follows Newton's second law. Force equals mass times acceleration. Acceleration happens all around us. When you press the gas pedal in a car, it speeds up. This is positive acceleration. When you hit the brakes, the car slows down. This is negative acceleration, also called deceleration. Even turning a corner at the same speed involves acceleration because the direction is changing. One of the most common types of acceleration is caused by gravity. Near Earth's surface, all falling objects accelerate at 9.8 meters per second squared, regardless of their mass. This means that each second an object falls, it moves faster and faster. If air resistance is ignored, a heavy rock and a feather would hit the ground at the same time. Acceleration is key in understanding motion in physics, engineering, and even space travel. Rockets must accelerate to escape Earth's gravity, athletes train to improve acceleration in sports, and roller coasters rely on rapid changes in acceleration to create thrilling rides. Whether on Earth or in the vastness of space, acceleration is a fundamental concept that governs movement and force. Level 9. Newton's laws of motion. Newton's three laws of motion describe how objects move and interact with forces. These laws, formulated by Sir Isaac Newton, form the foundation of classical physics and explain everything from falling objects to rocket launches. Newton's first law, the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This means that without friction or resistance, a rolling ball would keep moving forever. It's why you feel a jolt forward when a car suddenly stops. The body wants to keep moving even when the car comes to a halt. Newton's second law, force and acceleration. It explains that the acceleration of an object depends on the force applied to it and its mass. The greater the force, the greater the acceleration. This is why pushing an empty shopping cart is easier than pushing a full one. More mass requires more force to move. Newton's third law, action and reaction, states that for every action, there is an equal and opposite reaction. When you jump off the ground, your legs push downward, and the ground pushes you back up. This law is also why rockets work. Hot gases push downward, and in response, the rocket is propelled upward into space. These three laws govern all motion, from simple daily activities to the movement of planets. They help engineers design vehicles, predict how objects will behave, and even explain the forces that shape the universe. Newton's laws are a fundamental part of understanding how forces and motion interact in the physical world. Level 10. Velocity versus speed. Speed and velocity both describe how fast something moves, but velocity tells us something more: direction. While speed is simply the rate at which an object covers distance, velocity is a vector quantity, meaning it includes both speed and direction. Imagine a car moving at 60 kilometers per hour. If we only know this number, we are describing its speed. But if we say the car is moving at 60 kilometers per hour east, we are describing its velocity. This distinction is crucial in physics because two objects can have the same speed, but different velocities if they move in different directions. Velocity changes when either the speed or direction of an object changes. If a car moves in a straight line at a constant speed, its velocity remains the same. But if it turns left or right, even without changing speed, its velocity changes because the direction is different. This is why an object moving in a circular path, like a planet orbiting the Sun, is constantly changing velocity, even if its speed stays constant. Understanding the difference between speed and velocity is essential in physics, engineering, and navigation. Pilots, sailors, and even GPS systems rely on velocity to determine not just how fast something moves, but where it's going. Whether tracking a storm, launching a spacecraft, or predicting motion, velocity gives a complete picture of an object's movement. Level 11. Work and power. Work and power are two fundamental concepts that describe how energy is transferred and used. In physics, work is done when a force is applied to an object and causes it to move in the direction of that force. It is calculated using the formula work equals force multiplied by distance. This means that if you push a box across a room, you are doing work. However, if you push against a wall and it doesn't move, no work is done, even if you exert a lot of effort. Work is measured in joules, the unit of energy. Power measures how quickly work is done. It tells us how much energy is used per unit of time. The formula for power is power equals work divided by time. Power is measured in watts, named after James Watt, the inventor of the steam engine. A single watt is equal to 1 joule of work done per second. This is why a 100-watt light bulb uses energy faster than a 50-watt bulb. Work and power are all around us. Lifting weights at the gym requires work, but lifting them faster requires more power. A car with a powerful engine can accelerate quickly because it does more work in less time. Even household appliances are rated by power. Higher wattage means they use energy at a faster rate. Understanding work and power helps us design more efficient machines, improve energy use, and even understand the forces that drive everything, from human movement to massive industrial systems. Level 12. Conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed, only transferred or transformed. This fundamental principle of physics explains how energy moves through the universe, from the smallest atomic reactions to massive cosmic events. Energy comes in many forms such as kinetic energy, the energy of motion, potential energy, which is stored energy, thermal energy, which is heat, and electrical energy. No matter how energy changes form, the total amount of energy in a closed system always remains constant. A simple example is a swinging pendulum. At its highest point, the pendulum has maximum potential energy. As it swings downward, that energy transforms into kinetic energy, making it move faster. As it reaches the opposite peak, the kinetic energy is converted back into potential energy. This cycle continues, with small energy losses due to air resistance and friction, which are converted into thermal energy. This principle applies to all energy transfers. When you eat food, your body converts chemical energy into kinetic energy for movement and thermal energy to maintain body heat. In power plants, mechanical energy from turbines is converted into electrical energy to power homes. Even in space, nuclear fusion in stars transforms nuclear energy into light and heat, sustaining life on Earth. The conservation of energy is a key idea in science and engineering, helping us understand how machines work, how ecosystems function, and how energy can be harnessed more efficiently. It's a law that governs everything, proving that energy is never lost. It just changes form. Level 13. Heat versus temperature. Heat and temperature are closely related, but they are not the same thing. Temperature measures how hot or cold something is, while heat is the transfer of energy due to a temperature difference. Temperature is a measure of the average kinetic energy of particles in a substance. The faster the particles move, the higher the temperature. It is measured in degrees Celsius, Fahrenheit, or Kelvin. A cup of boiling water and a pot of boiling water can have the same temperature, even though the pot contains much more total energy. Heat, on the other hand, is energy in motion. It flows from hotter objects to colder objects until they reach thermal equilibrium. If you place an ice cube in your hand, heat flows from your warm hand into the ice, causing it to melt. This transfer of energy is measured in joules or calories. Heat moves in three ways: conduction, where energy transfers through direct contact, like a metal spoon heating up in hot soup; convection, where heat moves through fluids or gases, like warm air rising in a room; and radiation, where energy travels as electromagnetic waves, like heat from the sun warming your skin. Understanding the difference between heat and temperature helps explain how weather patterns form, how engines work, and even why metals feel colder than wood, even at the same temperature. Heat is energy in transit, while temperature tells us how much energy is present in a substance. Level 14. Thermal expansion. Thermal expansion is the tendency of materials to expand when heated and contract when cooled. This happens because heat increases the kinetic energy of particles, causing them to move faster and spread apart, making the material take up more space. This effect can be seen everywhere. Metal bridges have expansion joints to prevent damage when they expand in hot weather. Railway tracks have small gaps to allow for expansion so they don't warp. Even everyday objects like thermometers rely on thermal expansion. When the liquid inside is heated, it expands and rises, indicating a higher temperature. Different materials expand at different rates. Metals, gases, and liquids generally expand more than solids. In hot air balloons, heated air expands and becomes less dense, making the balloon rise. In contrast, when substances cool, their particles lose energy, move closer together, and the material contracts. This is why power lines sag in summer and tighten in winter. One unusual exception is water. Most substances contract as they cool, but water expands when it freezes, forming ice that is less dense than liquid water. This is why ice floats and why frozen pipes can burst in winter. Thermal expansion is a key concept in engineering, construction, and even space travel. Understanding it allows scientists to design materials that can withstand temperature changes, ensuring the safety and stability of buildings, machines, and even everyday appliances. Level 15. Friction. Friction is the force that resists motion when two surfaces come into contact. It occurs because even the smoothest surfaces have microscopic irregularities that create resistance as they move against each other. Without friction, walking, driving, and even holding objects would be impossible. There are several types of friction. Static friction keeps objects at rest until a force is strong enough to overcome it, like trying to push a heavy box that won't budge. Kinetic friction occurs when objects slide against each other, such as when a hockey puck moves across the ice. Rolling friction is much weaker and allows wheels to turn efficiently, which is why cars and bicycles are designed with wheels rather than flat surfaces. Fluid friction occurs when objects move through liquids or gases, like a swimmer pushing through water or an airplane gliding through air. Friction generates heat, which is why rubbing your hands together warms them up. It also causes wear and tear, making machine parts grind down over time. Engineers use lubricants like oil to reduce friction, helping engines and machines run smoothly. In contrast, friction is sometimes increased when needed, like using sandpaper to smooth wood or treaded tires for better grip on roads. Though friction can slow things down, it is essential for movement and control. Without it, cars wouldn't be able to stop, pencils wouldn't write, and we wouldn't be able to walk without slipping. Understanding friction helps in designing safer roads, more efficient machines, and even improving athletic performance. Level 16. Electromagnetism. Electromagnetism is one of the fundamental forces of nature, responsible for both electricity and magnetism. It explains how charged particles interact, how electric currents create magnetic fields, and how magnets can generate electricity. This force is essential to everything from household electronics to the structure of atoms. At its core, electricity is the movement of charged particles, usually electrons. When electrons flow through a conductor, like a wire, they create an electric current. This is how power is transmitted to homes, how batteries work, and how lightning forms in storms. Magnetism, on the other hand, comes from the movement of these charges. When electric current flows, it creates a magnetic field around it. This is the principle behind electromagnets. When electricity passes through a coil of wire, it generates a magnetic field strong enough to lift metal objects, power electric motors, and even operate MRI machines. The relationship between electricity and magnetism was discovered by James Clerk Maxwell, whose equations describe how these forces interact. One of the most important discoveries in electromagnetism is electromagnetic induction, discovered by Michael Faraday. This principle states that a changing magnetic field can produce an electric current, which is the basis for power generators and transformers. Electromagnetism is all around us. It enables communication through radios and Wi-Fi, powers transportation through electric motors, and even governs how atoms hold together. Without electromagnetism, modern technology, computers, televisions, and even the internet would not exist. It is a force that shapes both the natural world and human innovation. Level 17. Waves and Oscillations. Waves and oscillations are fundamental to how energy moves through the universe. Oscillations are repetitive motions, like a swinging pendulum or a vibrating guitar string. Waves are disturbances that transfer energy through space or a medium, often caused by oscillations. There are two main types of waves: mechanical waves and electromagnetic waves. Mechanical waves require a medium, like air, water, or solids, to travel through. Sound waves move through air by compressing and expanding air molecules, while ocean waves travel through water due to the movement of water particles. Mechanical waves can be further divided into transverse waves, where particles move perpendicular to the wave's direction, like ripples on a pond, and longitudinal waves, where particles move parallel to the wave's direction, like sound waves. Electromagnetic waves, on the other hand, do not need a medium and can travel through the vacuum of space. Light, radio waves, X-rays, and microwaves are all forms of electromagnetic waves, carrying energy through oscillating electric and magnetic fields. Key properties of waves include wavelength, the distance between two wave peaks, frequency, how many waves pass a point per second, and amplitude, the wave's height which determines energy or intensity. Higher frequency means more energy, which is why X-rays can penetrate the body, while radio waves cannot. Waves and oscillations are everywhere. They allow us to hear sound, see light, transmit information through radio signals, and even detect earthquakes. From music to Wi-Fi to seismic activity, understanding waves and oscillations helps us navigate and control the world around us. Level 18. Optics and Light. Optics is the study of light and its interactions with different materials, shaping how we see the world. Light is a form of electromagnetic radiation, meaning it travels in waves but also behaves like tiny particles called photons. This dual nature of light is fundamental to both classical and quantum physics. Light travels in straight lines until it interacts with objects, where it can be reflected, refracted, or absorbed. Reflection occurs when light bounces off a surface, like a mirror. Refraction happens when light bends as it passes through different materials, like a straw appearing bent in a glass of water. This bending of light allows lenses in glasses, microscopes, and telescopes to focus and magnify images. Light behaves differently depending on its wavelength. The visible spectrum, from red to violet, is the small range of light waves our eyes can see. Beyond this, infrared light is used in heat sensors, while ultraviolet light can cause sunburns. Even X-rays and radio waves are forms of light, just at wavelengths beyond human vision. Optics is essential in technology and science. It enables everything from fiber optic communication to laser surgery, from camera lenses to the study of distant galaxies. Light not only reveals the universe to us, but also drives innovation, making optics one of the most important fields in physics. Level 19. Sound and Acoustics. Sound is a mechanical wave that travels through a medium, such as air, water, or solids, by causing particles to vibrate. These vibrations create areas of compression and rarefaction, forming longitudinal waves that carry energy. The study of how sound is produced, transmitted, and received is known as acoustics. Sound has several key properties. Frequency, measured in hertz, determines the pitch. Higher frequencies create higher pitched sounds, while lower frequencies produce deeper tones. Amplitude refers to the wave's height and affects volume. Larger amplitudes result in louder sounds. Speed of sound depends on the medium, traveling fastest in solids, slower in liquids, and slowest in gases. For example, sound moves at about 343 meters per second in air, but much faster through water and even faster through metal. Sound can be reflected, absorbed, or refracted. Echoes occur when sound waves bounce off surfaces, while materials like foam absorb sound, reducing noise. This is why concert halls and recording studios use acoustic design to enhance or control sound. Acoustics plays a crucial role in everyday life, from music and speech to medical imaging and sonar technology. Understanding sound allows us to develop better speakers, noise-canceling headphones, and even ultrasound machines, which use high-frequency sound waves to create images inside the human body. Whether in communication, engineering, or nature, sound is a powerful force that shapes how we experience the world. Level 20. Atomic structure. Atoms are the building blocks of all matter. Everything around us, from the air we breathe to the stars in the sky, is made up of atoms. Despite being incredibly small, atoms have a complex internal structure composed of three main subatomic particles: protons, neutrons, and electrons. At the center of every atom is the nucleus, which contains protons and neutrons. Protons have a positive charge, while neutrons have no charge. The number of protons in an atom determines what element it is. For example, hydrogen has 1 proton, while carbon has 6. Surrounding the nucleus are electrons, which have a negative charge and move in regions called electron shells, or orbitals. These electrons determine how atoms interact and form chemical bonds. Atoms are mostly empty space. If the nucleus were the size of a marble, the outermost electron shell would be a football field away from it. Despite this, the electromagnetic forces between protons and electrons hold the atom together. Different atoms can combine to form molecules and compounds, shaping everything in the universe. Scientists also study isotopes, which are atoms of the same element with different numbers of neutrons, and ions, which are atoms that have gained or lost electrons, affecting their charge. Understanding atomic structure is crucial in chemistry, physics, and even biology. It explains how elements react, how electricity flows, and even how nuclear energy is produced. The study of atoms has led to groundbreaking advancements in medicine, materials science, and quantum mechanics, making atomic structure one of the most fundamental concepts in science. Level 21. The periodic table. The periodic table is the organized chart of all known elements, providing a powerful tool for understanding chemistry. Each element represents a different type of atom, defined by its number of protons in the nucleus. The table arranges these elements based on their atomic structure, properties, and chemical behavior. Developed by Dmitry Mendeleev in 1869, the periodic table is structured into rows and columns. The rows, called periods, indicate increasing atomic number, while the columns, called groups or families, contain elements with similar chemical properties. For example, alkali metals in group 1 are highly reactive, while noble gases in group 18 are stable and non-reactive. Each element's box contains key information: its atomic number, the number of protons, chemical symbol, and atomic mass. Elements are classified into metals, non-metals, and metalloids. Metals found on the left side of the table are shiny, conductive, and malleable. Non-metals on the right tend to be brittle and poor conductors, while metalloids have properties of both. The periodic table helps predict how elements interact, forming compounds that make up everything from water to DNA. It also reveals trends in reactivity, electronegativity, and atomic size. Scientists use it to discover new elements, develop new materials, and understand the fundamental principles of chemistry. The periodic table is more than just a list of elements. It is a roadmap to understanding matter, explaining the patterns and behaviors that govern the physical world. Level 22. Chemical bonds. Chemical bonds are the forces that hold atoms together, allowing them to form molecules and compounds. These bonds determine the structure, stability, and properties of everything from water to DNA. The three main types of chemical bonds are ionic, covalent, and metallic bonds. Ionic bonds form when atoms transfer electrons from one to another. This usually happens between metals and nonmetals. One atom loses electrons to become a positively charged ion, while the other gains electrons to become an ion that is negatively charged. These opposite charges attract, creating a strong bond. Common table salt, sodium chloride, is an example, where sodium donates an electron to chlorine, forming a stable compound. Covalent bonds occur when atoms share electrons instead of transferring them. This happens mostly between nonmetals and creates strong, stable molecules. Water forms because oxygen shares electrons with hydrogen atoms. Covalent bonds can be single, double, or triple, depending on how many pairs of electrons are shared. Metallic bonds exist in metals, where atoms share electrons in a way that allows them to move freely. This sea of electrons makes metals conduct electricity, bend without breaking, and have a shiny appearance. This is why materials like copper and aluminum are widely used in wiring and construction. Chemical bonds explain why substances have different melting points, conduct electricity, or dissolve in water. Understanding them is key to fields like medicine, engineering, and material science, helping scientists design new medicines, stronger materials, and advanced technologies. Level 23. Chemical reactions. A chemical reaction is a process where substances are transformed into new substances with different properties. This occurs when chemical bonds are broken, formed, or rearranged, leading to a change in composition, energy, or appearance. Chemical reactions power everything from digestion to combustion and even the processes inside stars. Every reaction follows the basic principle of the law of conservation of mass, which states that matter cannot be created or destroyed, only rearranged. This means the number of atoms in the reactants always equals the number in the products, just in a different form. Chemical reactions can be classified into several types. Synthesis reactions combine simpler substances to form a more complex compound, like hydrogen and oxygen forming water. Decomposition reactions break down a compound into simpler substances, like electrolysis, splitting water into hydrogen and oxygen. Combustion reactions release energy when a substance reacts with oxygen, as seen in burning fuel. Replacement reactions occur when elements swap places within compounds, like rust forming when iron reacts with oxygen. Reactions can either absorb energy, like photosynthesis, or release energy, like burning wood. The rate of a reaction depends on temperature, concentration, surface area, and the presence of catalysts, which speed up reactions without being consumed. Chemical reactions are fundamental to life and technology. They allow plants to convert sunlight into food, power vehicles through combustion, and enable industries to create everything from medicines to plastics. Understanding chemical reactions helps us control, harness, and apply chemistry to improve the world around us. Level 24. Photosynthesis. Photosynthesis is the process by which plants, algae, and some bacteria convert sunlight into chemical energy, sustaining almost all life on Earth. Using carbon dioxide, water, and sunlight, plants produce glucose, which is a form of sugar, and oxygen, which fuels ecosystems and replenishes the atmosphere with breathable air. This process takes place in the chloroplasts of plant cells, specifically in structures called thylakoids, which contain the green pigment chlorophyll. Chlorophyll absorbs light energy from the sun, primarily in the blue and red wavelengths, while reflecting green light, giving plants their color. Photosynthesis occurs in two stages, the light-dependent reactions and the Calvin cycle. In the light-dependent reactions, sunlight is absorbed and its energy is used to split water molecules, releasing oxygen gas and generating ATP and NADPH, the energy carriers that power the next stage. In the Calvin cycle, these energy molecules drive a series of chemical reactions that convert carbon dioxide into glucose, which plants use for growth and energy storage. Photosynthesis is essential for maintaining Earth's ecosystems. It not only produces the oxygen we breathe, but also forms the base of the food chain, supporting all herbivores and indirectly carnivores. Additionally, it helps regulate the planet's carbon cycle, absorbing CO2 from the atmosphere and mitigating climate change. Without photosynthesis, life as we know it would not exist, making it one of the most important biochemical processes on Earth. Level 25. Cellular Respiration. Cellular respiration is the process by which cells convert glucose and oxygen into usable energy, fueling essential biological functions. This occurs in three main stages: glycolysis, which breaks down glucose in the cytoplasm, the Krebs cycle, where high-energy electrons are extracted, and the electron transport chain, where most ATP, the cell's energy currency, is generated. This process primarily takes place in the mitochondria, often called the powerhouse of the cell. Oxygen acts as the final electron acceptor, allowing efficient ATP production, while carbon dioxide and water are released as byproducts. The energy generated powers everything from muscle movement to brain function, ensuring that cells operate efficiently. Without cellular respiration, life as we know it wouldn't be possible. It enables organisms to extract energy from food, sustaining growth, repair, and daily activities at the cellular level. Whether in humans, plants, or microorganisms, this process is fundamental to all living systems. Level 26. Plate tectonics. Plate tectonics is the theory that Earth's outer shell, the lithosphere, is divided into large, rigid plates that move over the semi-fluid asthenosphere beneath them. This movement shapes the Earth's surface, causing earthquakes, volcanic activity, and the formation of mountains and ocean basins. The lithosphere is broken into 7 major plates and many smaller ones, including the Pacific, North American, Eurasian, and African plates. These plates move slowly at rates of a few centimeters per year, driven by heat from the Earth's core through a process called mantle convection. There are 3 main types of plate boundaries: divergent, convergent, and transform. At divergent boundaries, plates move apart, creating new crust as magma rises, such as along the mid-Atlantic ridge. At convergent boundaries, plates collide, and one may be forced beneath the other in a process called subduction, forming deep-sea trenches and volcanic mountain ranges, like the Andes or the Himalayas. At transform boundaries, plates slide past each other, causing earthquakes along faults like the San Andreas Fault in California. Plate tectonics explains continental drift, the idea that continents slowly move over time. Millions of years ago, Earth's landmasses were joined in a supercontinent called Pangaea, which later split apart due to plate movement. This process is responsible for volcanic eruptions, mountain building, and ocean formation, shaping Earth's surface over geological time. Understanding plate tectonics is crucial for predicting earthquakes, managing natural hazards, and uncovering Earth's history through fossil and rock evidence. It is one of the most important theories in geology, explaining the dynamic nature of our planet. Level 27. Seismic wave propagation. Seismic wave propagation is how energy travels through Earth's interior and surface during earthquakes and geological events. These waves help scientists study Earth's structure and predict seismic activity. There are 2 main types: body waves and surface waves. Body waves travel through Earth's interior and include P waves, which move fastest in a compressional motion, and S waves, which create a shearing effect but cannot pass through liquids. Surface waves, like Love waves and Rayleigh waves, move along Earth's exterior and cause the most damage during earthquakes. By analyzing how these waves bend and reflect, geophysicists can map Earth's layers and detect hidden fault lines. Seismic wave studies are key for early warning systems, earthquake preparedness, and planetary exploration, helping us understand the dynamic forces shaping our world. Level 28. Ecological network theory and system stability. Ecological network theory explores how species interact within ecosystems, forming complex, interconnected networks that determine stability and resilience. Just like a web, every species, whether predator, prey, or mutualistic partner, plays a role in maintaining ecological balance. Disrupting one part of the system can lead to cascading effects, altering biodiversity and ecosystem function. These networks are classified into trophic networks, mutualistic networks, and competition networks. In a food web, energy flows from primary producers like plants to herbivores, predators, and decomposers. Mutualistic interactions such as bees pollinating flowers enhance biodiversity and ecosystem productivity. When competition occurs, such as between species for resources, stability depends on how well organisms can adapt or coexist. System stability depends on connectivity and redundancy. The more interconnected an ecosystem is, the more likely it is to resist disturbances like climate change, habitat destruction, or species extinction. However, if key species, known as keystone species, disappear, the entire system may collapse. For example, removing top predators can lead to uncontrolled prey populations, disrupting the entire food chain. Mathematical models help scientists predict how ecosystems respond to change, guiding conservation efforts, habitat restoration, and sustainable resource management. Understanding ecological networks is crucial for protecting biodiversity, ensuring food security, and mitigating environmental crises. By studying these intricate relationships, we can better preserve the delicate balance that sustains life on Earth. Level 29. Symbiosis. Symbiosis is a long-term interaction between different species where at least one benefits. These relationships are fundamental to ecosystems, influencing survival, reproduction, and resource distribution. The three main types are mutualism, commensalism, and parasitism. Mutualism benefits both species. Bees pollinate flowers while collecting nectar, ensuring plant reproduction, and clownfish find shelter in sea anemones while defending them from predators. Commensalism benefits one species while leaving the other unaffected, such as barnacles attaching to whales for transport or orchids growing on trees to access more sunlight. Parasitism benefits one species at the expense of another. Ticks, fleas, and tapeworms extract nutrients from their hosts, sometimes causing disease. Symbiotic relationships promote biodiversity, ecological balance, and resource efficiency. Some, like gut bacteria aiding digestion, are essential for survival, while others, like parasites, help regulate populations. Understanding symbiosis aids conservation, medicine, and agriculture, highlighting the deep interconnections that sustain life on Earth. Level 30. Microbial life. Microbial life consists of microscopic organisms, including bacteria, viruses, fungi, protists, and archaea. Though invisible to the naked eye, microbes are the most abundant life forms on Earth, playing vital roles in ecosystems, human health, and biotechnology. Bacteria are single-celled prokaryotes that thrive in diverse environments, from soil to deep-sea vents. Some bacteria are beneficial, such as gut microbiota that aid digestion, while others, like Salmonella, can cause disease. Bacteria reproduce rapidly through binary fission and can exchange genetic material through horizontal gene transfer, allowing them to develop antibiotic resistance. Viruses are non-living infectious agents that require a host cell to replicate. They consist of genetic material enclosed in a protein coat. Viruses like influenza and HIV hijack host cells to reproduce, while others, like bacteriophages, infect bacteria. Fungi, including molds and yeasts, decompose organic matter and form symbiotic relationships with plants. Protists, a diverse group of eukaryotic microbes, include amoebas, algae, and malaria-causing plasmodium. Archaea, similar to bacteria but genetically distinct, thrive in extreme conditions like hot springs and deep-sea hydrothermal vents. Microbes are essential to life. They cycle nutrients, decompose waste, and even produce oxygen through photosynthetic bacteria, like cyanobacteria. In medicine, microbes contribute to antibiotic production, vaccines, and microbiome research. In industry, they aid in fermentation, biofuel production, and genetic engineering. While some microbes cause diseases, many are essential for health and the environment. Studying microbial life helps scientists develop new treatments, improve agriculture, and understand the origins of life on Earth, and even the possibility of life on other planets. Level 31. Natural selection. Natural selection is the process by which organisms with traits best suited to their environment survive and reproduce, passing those traits to the next generation. Proposed by Charles Darwin, it is the driving force behind evolution, shaping species over time. The process works through variation, competition, and adaptation. Within a population, individuals have genetic differences due to mutations and recombination. Some of these traits provide advantages, like better camouflage, faster speed, or disease resistance, while others may be neutral or harmful. Because resources like food and shelter are limited, organisms compete to survive. Those with beneficial traits are more likely to reproduce, a concept known as survival of the fittest. Over generations, these traits become more common, leading to adaptation, where a population becomes better suited to its environment. Natural selection explains how peppered moths in industrial England evolved from light to dark as pollution darkened tree bark, making dark moths harder for predators to spot. It also accounts for antibiotic resistance in bacteria, where only the strongest survive and pass on their resistant genes. This ongoing process shapes life on Earth, explaining species diversity from the speed of cheetahs to the beaks of Darwin's finches. Understanding natural selection helps scientists study evolution, track disease resistance, and predict species adaptation to environmental changes. Level 32. Artificial selection. Artificial selection, or selective breeding, is the process by which humans breed organisms to enhance specific traits. Unlike natural selection, which occurs without human intervention, this method allows people to shape plant and animal characteristics over generations. For thousands of years, domesticated animals like dogs, cattle, and horses have been bred for traits such as speed, strength, or temperament. Modern dog breeds, from Chihuahuas to Great Danes, all descend from wolves but were selectively bred for different purposes. In agriculture, farmers breed crops to improve yield, disease resistance, and nutrition. Corn, for instance, was cultivated from a wild grass called teosinte into the large, edible kernels we eat today. Many modern fruits and vegetables have been altered to be larger, sweeter, and more appealing. Artificial selection can involve traditional breeding or genetic modification. While selective breeding takes generations, genetic engineering allows scientists to directly modify DNA to introduce desirable traits, like pest resistance in crops or faster growth in livestock. However, artificial selection has risks. Reduced genetic diversity makes populations more vulnerable to disease and environmental changes. Many purebred dogs, for example, suffer from inherited health problems due to excessive inbreeding. Despite challenges, artificial selection has shaped civilization, improving food production, domesticated animals, and medical research. Understanding this process helps scientists and farmers balance efficiency, sustainability, and ethics in agriculture and animal breeding. Level 33. Fossil record and evolution. The fossil record is a collection of preserved remains, traces, or imprints of past organisms, providing direct evidence of evolution. By studying fossils, scientists reconstruct extinct species, track adaptations, and understand evolutionary relationships over millions of years. Fossils form when organisms are buried under sediment and preserved through mineralization, compression, or freezing. Over time, these remains turn into rock, creating a timeline of life. According to Superposition, fossils found in deeper rock layers are older, helping scientists date evolutionary changes. The fossil record reveals major transitions. Transitional fossils like Archaeopteryx, which has both reptilian and bird-like traits, support the evolution of birds from dinosaurs. Similarly, Tiktaalik shows the shift from fish to amphibians, bridging aquatic and land-dwelling life. Patterns in fossils support Darwin's theory of evolution, showing how life evolved from simpler to more complex forms. They also document mass extinctions and the emergence of new species, illustrating how natural selection and environmental shifts shape biodiversity. Though fossilization is rare, advances in paleontology, radiometric dating, and genetic analysis continue refining our understanding of evolutionary history. Fossils remain a crucial link to Earth's past, helping scientists trace ancestry and uncover the origins of modern species, including humans. Level 34. States of Equilibrium. Equilibrium is the state in which opposing forces or influences are balanced, leading to stability in a system. In physics and chemistry, equilibrium plays a crucial role in maintaining balance in mechanical systems, chemical reactions, and even biological processes. In mechanical equilibrium, an object remains at rest or moves at a constant velocity because all forces acting on it are balanced. If the sum of all forces equals zero, the object does not accelerate. A book resting on a table or a car cruising at a steady speed are examples of mechanical equilibrium. In chemical equilibrium, reactions occur at the same rate in both directions, meaning the concentrations of reactants and products remain constant over time. This does not mean the reaction has stopped. Molecules are continuously reacting, but their overall amounts stay the same. A good example is the balance between carbon dioxide and oxygen in the blood, which helps regulate breathing. There are three main types of equilibrium: stable, unstable, and neutral. In stable equilibrium, if an object is slightly disturbed, it returns to its original position, like a pendulum at rest. In unstable equilibrium, a small disturbance causes the system to move further away from its balance point, like a pencil standing on its tip. In neutral equilibrium, an object remains balanced no matter how it is moved, like a ball resting on a flat surface. Equilibrium is essential in engineering, chemistry, and nature. It governs everything from the balance of forces in bridges and buildings to the regulation of ecosystems and climate. Understanding equilibrium helps scientists and engineers design stable systems, ensuring efficiency and sustainability in everything from industrial processes to human physiology. Level 35. The conservation of mass. The law of conservation of mass states that matter cannot be created or destroyed in a closed system. It can only change form. This means that during any chemical or physical process, the total mass of the reactants must equal the total mass of the products. This principle, first established by Antoine Lavoisier in the 18th century, is a fundamental law of chemistry and physics. In chemical reactions, atoms are rearranged but never disappear. For example, when wood burns, it turns into ash, smoke, and gases. But if you could collect all the particles and gases, the total mass would remain the same. Similarly, when water evaporates into steam, the amount of matter remains constant. It just changes from liquid to gas. This law also applies to nuclear reactions, although mass can be converted into energy according to Einstein's equation, E equals mc squared. However, the total amount of mass and energy combined still remains constant. The conservation of mass is essential in scientific calculations. In chemistry, it helps balance equations to ensure that the number of atoms remains the same before and after a reaction. In engineering, it ensures the proper design of chemical plants, fuel combustion, and environmental processes like the carbon cycle. Understanding the conservation of mass allows scientists and engineers to predict outcomes, create new materials, and develop sustainable processes. It proves that matter is never lost, only transformed into different forms, shaping the natural and technological world around us. Level 36. Isotopes and radioactivity. Isotopes are different forms of the same element that have the same number of protons, but different numbers of neutrons in their nuclei. This difference in neutron count affects the mass of the atom, but does not change its chemical properties. Some isotopes are stable, while others are radioactive, meaning they decay over time and release energy in the form of radiation. For example, carbon has multiple isotopes. Carbon-12 is stable, while carbon-14 is radioactive and used in carbon dating to determine the age of ancient artifacts. Similarly, uranium-235 is a radioactive isotope used in nuclear power and atomic bombs because of its ability to sustain chain reactions. Radioactive isotopes undergo radioactive decay, where they emit alpha, beta, or gamma radiation. Alpha particles are large and can be blocked by paper. Beta particles are smaller and can pass through paper, but are stopped by metal. Gamma rays are highly energetic electromagnetic waves that can penetrate deep into materials, requiring thick lead or concrete for shielding. Radioactivity has many uses. It helps in medical treatments like radiation therapy for cancer and in nuclear energy, where controlled reactions generate electricity. It also plays a role in scientific research, from dating fossils to studying cosmic radiation. However, excessive exposure to radiation can be harmful, as it can damage living cells and DNA, leading to health risks like radiation sickness and cancer. Understanding isotopes and radioactivity allows scientists to harness nuclear energy, develop medical treatments, and study the fundamental forces of nature. While radiation can be dangerous, controlled use of isotopes has transformed medicine, energy production, and our understanding of the universe. Level 37. Entropy and the second law of thermodynamics. Entropy is a measure of disorder or randomness in a system, and it is a key concept in thermodynamics. The second law of thermodynamics states that in any natural process, the total entropy of a closed system always increases over time. In simple terms, energy naturally spreads out, and systems tend to move from order to disorder unless energy is added to maintain structure. A classic example of entropy is melting ice. A solid block of ice has highly ordered water molecules, but as it melts, those molecules spread out into a more disordered liquid state. Similarly, if you drop a glass, it shatters into many pieces, increasing disorder, yet it never spontaneously reassembles itself. Entropy also explains why heat flows from hot objects to cold ones, and never the other way around. A hot cup of coffee cools down because its thermal energy spreads out into the surrounding air. This one-way direction of energy transfer defines the arrow of time, meaning that time naturally moves forward as entropy increases. Despite entropy's tendency toward disorder, life defies this locally. Living organisms maintain order by constantly using energy, such as the food we eat or the sunlight plants absorb. However, this does not violate the second law. Organisms reduce their own entropy by increasing entropy elsewhere, such as by releasing heat. Entropy affects everything from chemical reactions and engine efficiency to the expansion of the universe. Scientists believe that at the beginning of time, the universe had low entropy, and as it expands, entropy continues to increase. Understanding entropy and the second law of thermodynamics helps explain why energy cannot be fully recycled, why machines are never 100% efficient, and why the universe moves toward greater disorder over time. Level 38. Gas laws. The gas laws describe how gases behave under different conditions of pressure, volume, and temperature. These laws explain everything from how balloons expand to how air pressure changes with altitude. The three main gas laws are combined in the ideal gas law equation. Boyle's law states that pressure and volume are inversely related when temperature is constant. If you decrease the volume of a gas, its pressure increases. This is why squeezing a balloon makes it shrink. Reducing space forces the gas molecules closer together, increasing pressure. Charles's law states that volume and temperature are directly related when pressure is constant. As temperature increases, gas expands. This is why a hot air balloon rises. Heating the air inside causes it to expand, making it less dense and allowing it to float. Gay-Lussac's law states that pressure and temperature are directly related when volume is constant. Heating a sealed gas container increases pressure, which is why aerosol cans warn against being left in high heat. They could explode from the rising pressure. Gas laws explain how our lungs expand and contract, how weather systems form, and even how rockets work in space. Understanding them is essential in engineering, meteorology, and chemistry, helping us control gases in everything from car engines to scuba tanks. Level 39, Electromagnetic Spectrum. The electromagnetic spectrum is the range of all types of electromagnetic waves, from radio waves to gamma rays. These waves travel at the speed of light and differ only in wavelength and frequency. The spectrum is essential in everything from communication to medical imaging and astronomy. At one end of the spectrum are radio waves, which have the longest wavelengths and lowest frequencies. They are used for radio, television, and Wi-Fi signals. Microwaves, slightly higher in frequency, are used for cooking food and satellite communications. Moving further, we reach infrared waves, which are responsible for heat. Night vision cameras detect infrared radiation, and remote controls use it to send signals. Visible light is the small part of the spectrum that humans can see, ranging from red, longer wavelength, to violet, shorter wavelength. Beyond visible light are ultraviolet rays, which are emitted by the sun and can cause sunburn. Higher in energy, X-rays can pass through soft tissue, making them useful in medical imaging. At the extreme end are gamma rays, which have the shortest wavelengths and highest energy, capable of penetrating deep into matter. They are produced by nuclear reactions and are used in cancer treatments. The electromagnetic spectrum is fundamental to modern technology. It enables wireless communication, medical advancements, and space exploration. From the light we see to the signals that power the internet, the spectrum is an invisible force that shapes our daily lives. Level 40, Nuclear Reactions. Nuclear reactions involve changes in the nucleus of an atom, releasing enormous amounts of energy. Unlike chemical reactions, which only involve electron interactions, nuclear reactions alter the protons and neutrons in an atom's core, often transforming one element into another. The two main types of nuclear reactions are nuclear fission and nuclear fusion. Nuclear fission occurs when a heavy nucleus splits into two or more smaller nuclei, releasing energy in the process. This reaction is used in nuclear power plants to generate electricity and in atomic bombs. When a neutron strikes a uranium-235 or plutonium-239 nucleus, it becomes unstable and splits, releasing more neutrons and triggering a chain reaction. This controlled chain reaction is what powers nuclear reactors. Nuclear fusion, on the other hand, occurs when two light nuclei combine to form a heavier nucleus, releasing even more energy than fission. This process powers the sun and other stars, where hydrogen atoms fuse to form helium under extreme temperatures and pressure. Scientists are working to harness fusion energy on Earth, as it could provide limitless clean energy without the radioactive waste produced by fission. Nuclear reactions also occur naturally in radioactive decay, where unstable atoms break down over time, emitting radiation in the form of alpha, beta, or gamma particles. This process is used in radiocarbon dating to determine the age of ancient artifacts. Nuclear reactions have revolutionized energy production, medicine, and scientific research. They power nuclear submarines, provide cancer treatments through radiation therapy, and help us understand the origins of the universe. While nuclear energy offers immense potential, it also requires careful management due to the risks of radiation and nuclear waste. Level 41, Quantum Mechanics Basics. Quantum mechanics is the branch of physics that describes the behavior of particles at the smallest scales, such as atoms and subatomic particles. Unlike classical physics, which follows predictable laws, quantum mechanics reveals a world where particles can exist in multiple states at once, teleport across space, and behave like both particles and waves. One of the most fundamental principles is wave-particle duality. Light, electrons, and other small particles can behave like waves in some situations and like particles in others. This was demonstrated in the double-slit experiment, where electrons fired through two slits created an interference pattern, acting like waves even when sent one at a time. Another key concept is quantum superposition, where particles exist in multiple states simultaneously until observed. This idea is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box can be both alive and dead until someone looks inside. Quantum entanglement is another strange phenomenon, where two particles become linked, no matter how far apart they are. A change in one particle instantly affects the other, seemingly violating the laws of classical physics. Einstein called this spooky action at a distance, but experiments have proven that entanglement is real. Quantum mechanics is the foundation of modern technology. It explains how semiconductors work, leading to computers, lasers, and quantum encryption. Scientists are also developing quantum computers, which use superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Though counterintuitive, quantum mechanics is one of the most successful theories in physics, shaping our understanding of the universe at its most fundamental level. It challenges reality itself, showing that the microscopic world operates in ways that defy our everyday experiences. Level 42. Wave-particle duality. Wave-particle duality is one of the most thought-provoking concepts in quantum mechanics. It states that particles, such as electrons and photons, can behave as both waves and particles, depending on how they are observed. This challenges classical physics, where something is either a wave or a particle, but never both. This concept was first demonstrated in the double-slit experiment. When electrons or photons are fired through two slits, they create an interference pattern, just like waves in water. This suggests they are behaving as waves. However, when scientists try to measure which slit each particle passes through, the interference pattern disappears, and the electrons act like individual particles instead. The simple act of observation changes their behavior. Wave-particle duality also applies to light. In some experiments, light behaves like a wave, bending around obstacles and creating interference. In other cases, it acts like a particle, as seen in the photoelectric effect, where light knocks electrons off a metal surface. Albert Einstein explained this by proposing that light consists of particles called photons that carry energy. This duality is not limited to light or electrons. All matter has wave-like properties, according to de Broglie's hypothesis. Even large objects technically have wavelengths, but they are too small to detect at macroscopic scales. Wave-particle duality is a fundamental principle of quantum mechanics, shaping our understanding of atoms, molecules, and even the nature of reality. It forms the basis for technologies like electron microscopes, quantum computing, and semiconductor physics, proving that at the quantum level, the universe doesn't follow the simple rules of everyday experience. Level 43. DNA and the genetic code. DNA, or deoxyribonucleic acid, is the molecule that carries the genetic instructions for all living organisms. It is the blueprint of life, determining everything from eye color to how cells function. Found in the nucleus of cells, DNA contains the genetic code, which directs growth, development, and reproduction. The structure of DNA is a double helix, resembling a twisted ladder. The sides of the ladder are made of sugar and phosphate molecules, while the rungs consist of 4 nitrogenous bases: adenine A, thymine T, cytosine C, and guanine G. These bases pair in a specific way. A always pairs with T, and C always pairs with G. The sequence of these bases forms the genetic instructions, just like letters in a book form words and sentences. The genetic code is read in triplets called codons, where every 3 bases correspond to a specific amino acid. Amino acids link together to form proteins, which are essential for building and repairing tissues, catalyzing biochemical reactions, and regulating bodily functions. DNA replication allows cells to divide and pass on genetic information. Errors in this process, known as mutations, can lead to genetic variations, some of which drive evolution, while others can cause diseases like cancer. Understanding DNA has revolutionized science and medicine. It enables genetic engineering, forensic science, disease research, and personalized medicine. The discovery of DNA's structure and function has unlocked the secrets of heredity and evolution, making it one of the most significant scientific breakthroughs of all time. Level 44. Mendelian Genetics. Mendelian genetics is the foundation of modern genetics, explaining how traits are inherited from one generation to the next. It is based on the work of Gregor Mendel, an Austrian monk who, in the 1860s, experimented with pea plants to uncover the basic principles of heredity. Mendel discovered that traits are controlled by genes, which come in different forms called alleles. Each organism inherits 2 alleles per gene, one from each parent. Some alleles are dominant, meaning they express their trait even if only one copy is present, while others are recessive, meaning they only show up if both copies are the recessive allele. Mendel formulated 3 fundamental laws of inheritance. The law of segregation. Each parent passes only one allele for a trait to their offspring, and these alleles separate randomly during reproduction. The law of independent assortment. Different traits are inherited independently of each other, meaning having blue eyes doesn't necessarily mean a person will have brown hair. The law of dominance. A dominant allele will always express its trait over a recessive allele if both are present. Mendelian genetics explains simple inheritance patterns seen in eye color, blood type, and certain genetic disorders. However, modern genetics has revealed that many traits are influenced by multiple genes and environmental factors, making inheritance more complex. Mendel's discoveries laid the groundwork for fields like genetic research, biotechnology, and medical genetics. Understanding these principles helps scientists study hereditary diseases, improve crops, and even explore gene editing through technologies like CRISPR. Level 45. Epigenetics. Epigenetics is the study of how genes can be turned on or off without changing the underlying DNA sequence. While traditional genetics focuses on the DNA code itself, epigenetics explores how environmental factors, lifestyle choices, and even experiences can influence which genes are active. At the core of epigenetics are chemical modifications that affect gene expression. One of the most well-known mechanisms is DNA methylation, where chemical tags called methyl groups attach to DNA, silencing certain genes. Another process, histone modification, changes how DNA is wrapped around proteins, making it easier or harder for genes to be read and expressed. Epigenetics explains why identical twins who have the same DNA can develop different traits, health conditions, or even personalities over time. Factors such as diet, stress, pollution, and exercise can all impact epigenetic markers, affecting how genes behave. For example, studies have shown that malnutrition in pregnant women can lead to epigenetic changes in their children, affecting metabolism and disease risk later in life. Epigenetic changes are reversible, meaning that lifestyle choices can sometimes modify gene expression. This has major implications for medicine, especially in cancer treatment, where scientists are developing drugs to target abnormal epigenetic patterns that turn healthy cells into cancerous ones. Epigenetics is revolutionizing our understanding of genetics, showing that genes are not destiny. It bridges the gap between nature and nurture, revealing how our environment and experiences can shape not just our own biology, but potentially the traits of future generations. Level 46. Neurotransmission. Neurotransmission is the process by which nerve cells, neurons, communicate with each other to send signals throughout the body. This system controls everything from movement and reflexes to thoughts and emotions, making it essential for brain function and nervous system activity. Neurons communicate using electrical and chemical signals. When a neuron receives a stimulus, it generates an electrical impulse called an action potential, which travels down the neuron's axon. At the end of the axon, the signal reaches a small gap between neurons called a synapse. Since electrical signals cannot cross the synapse, they are converted into chemical signals in the form of neurotransmitters, specialized molecules that transmit messages from one neuron to the next. Neurotransmitters are released from tiny sacs called vesicles into the synapse, where they bind to receptor sites on the next neuron. This triggers a response, either exciting the neuron to continue the signal or inhibiting it to prevent further transmission. Afterward, neurotransmitters are either broken down by enzymes, reabsorbed into the neuron, or diffused away to stop the signal. Different neurotransmitters play specific roles. Dopamine is involved in motivation and pleasure. Serotonin regulates mood and sleep. Acetylcholine controls muscle movement, and GABA calms the nervous system. Imbalances in neurotransmitters can lead to neurological and psychiatric disorders such as depression, Parkinson's disease, or anxiety. Understanding neurotransmission has led to advances in medicine and neuroscience, enabling the development of treatments for mental health disorders, neurodegenerative diseases, and even brain-machine interfaces. It is the foundation of how the brain and body work together, shaping our thoughts, behaviors, and interactions with the world. Level 47. Mutation and genetic variation. Mutation and genetic variation are the driving forces behind evolution and biological diversity. Mutations are changes in the DNA sequence, and they introduce genetic differences that can be passed from one generation to the next. While some mutations have no effect, others can be beneficial, harmful, or even lead to diseases. Mutations can occur in several ways. Point mutations involve a single change in a DNA base, while insertions or deletions add or remove genetic material, potentially altering how genes function. Some mutations happen naturally during DNA replication, while others are caused by external factors like radiation, chemicals, or viruses. Although mutations can sometimes lead to genetic disorders, they are also essential for adaptation and survival. Beneficial mutations can provide an advantage, such as resistance to diseases or the ability to digest new foods. Over generations, these changes accumulate, leading to evolutionary adaptations that shape entire species. Genetic variation, which comes from mutations, sexual reproduction, and genetic recombination, ensures that populations have diverse traits. This diversity helps species survive environmental changes. For example, some bacteria evolve antibiotic resistance through mutations, making them harder to kill. Scientists study mutations to understand genetic diseases, cancer development, and evolutionary history. Advances in gene editing technologies like CRISPR now allow scientists to modify DNA, potentially correcting harmful mutations before they cause disease. Mutation and genetic variation are the foundation of life's complexity. While some mutations cause problems, they also enable evolution, drive diversity, and allow organisms to adapt to an ever-changing world. Level 48. Homeostasis. Homeostasis is the process by which organisms maintain a stable internal environment, despite changes in external conditions. This balance is crucial for survival, ensuring that body temperature, pH, hydration, and other vital conditions remain within optimal ranges. The human body relies on feedback mechanisms to regulate homeostasis. Negative feedback loops are the most common, working like a thermostat to correct imbalances. For example, when body temperature rises, the brain signals sweat glands to cool the body. When temperature drops, shivering generates heat to restore warmth. Similarly, blood sugar levels are regulated by insulin and glucagon, which help maintain energy balance. Positive feedback loops, though less common, amplify changes rather than reverse them. An example is childbirth, where the hormone oxytocin increases contractions until delivery. Blood clotting is another example. When a vessel is damaged, platelets release signals to recruit more platelets, quickly sealing the wound. Homeostasis is vital across all living organisms. In plants, stomata regulate water loss and gas exchange, preventing dehydration. In marine life, osmoregulation helps fish control salt and water levels in different environments. Disruptions in homeostasis can lead to diseases such as diabetes, dehydration, or heat stroke, where the body fails to regulate critical functions. Medical advances like insulin therapy and dialysis help restore homeostasis in patients with chronic conditions. Homeostasis ensures that organisms function efficiently in changing environments. By maintaining internal stability, it allows life to adapt, survive, and thrive in diverse conditions, making it a fundamental principle of biology. Level 49. CRISPR Gene Editing. CRISPR gene editing is a revolutionary technology that allows scientists to precisely modify DNA in living organisms. CRISPR, which stands for Clustered Regularly Interspaced Short Palindromic Repeats, is based on a natural defense system found in bacteria that helps them recognize and destroy viral DNA. Scientists have adapted this system into a powerful tool for genetic engineering. At the core of CRISPR is the Cas9 enzyme, which acts like molecular scissors. A small piece of guide RNA directs Cas9 to a specific location in the genome, where it cuts the DNA. Once the DNA is cut, scientists can delete, modify, or insert new genetic material, allowing them to correct mutations, improve traits, or even create entirely new functions in organisms. CRISPR has huge implications for medicine, agriculture, and biotechnology. It offers the potential to cure genetic diseases like sickle cell anemia, cystic fibrosis, and even some cancers by repairing faulty genes. In agriculture, CRISPR is used to develop disease-resistant crops, drought-tolerant plants, and nutrient-enhanced foods. Scientists are also exploring CRISPR to fight infectious diseases, such as modifying mosquitoes to reduce the spread of malaria. Despite its promise, CRISPR raises ethical and safety concerns. Editing human embryos, for example, could lead to unintended genetic changes that pass to future generations. There are also risks of off-target effects, where unintended parts of the genome are altered. CRISPR is transforming genetic research and biotechnology, offering possibilities once thought impossible. As scientists refine this technology, it could revolutionize medicine, food production, and environmental conservation, making gene editing one of the most significant breakthroughs in modern science. Level 50. Synthetic Biology. Synthetic biology is the engineering of life, a field that combines biology, genetics, and technology to design and create new biological systems. Unlike traditional genetic modification, which involves altering existing genes, synthetic biology allows scientists to build entirely new DNA sequences, creating organisms with novel traits. At its core, synthetic biology works by designing, assembling, and programming DNA to give cells new functions. Scientists use tools like CRISPR and DNA synthesis to edit or create genes that do not exist in nature. This has led to breakthroughs such as bacteria that produce biofuels, yeast engineered to synthesize medicine, and crops that glow in the dark. One of the most significant applications is synthetic organisms, such as bacteria programmed to detect and fight diseases inside the human body. In medicine, synthetic biology is being used to create personalized gene therapies, synthetic vaccines, and lab-grown organs. Scientists have even synthesized a minimal genome, creating artificial life that can be programmed for specific tasks. Beyond medicine, synthetic biology is revolutionizing environmental science. Engineered microbes can break down plastic waste, absorb carbon dioxide, and clean up oil spills. In agriculture, scientists are developing nitrogen-fixing crops that reduce the need for fertilizers, making farming more sustainable. However, synthetic biology raises ethical and safety concerns. The ability to create life in a lab raises questions about bioterrorism, ecological disruption, and the unintended consequences of releasing synthetic organisms into nature. Regulation and oversight are needed to ensure this technology is used responsibly. Synthetic biology is pushing the boundaries of what is possible in science. It has the potential to cure diseases, combat climate change, and create entirely new forms of life, making it one of the most transformative fields in modern biology. Level 51, the Standard Model of Particle Physics. The Standard Model of particle physics is the framework that describes the fundamental particles and the forces that govern the universe. It explains how everything we see, from atoms to galaxies, is built from a small set of elementary particles and how they interact through fundamental forces. At the heart of the Standard Model are two main groups of particles, fermions and bosons. Fermions are the building blocks of matter and include quarks and leptons. Quarks combine to form protons and neutrons, while leptons include particles like electrons and neutrinos. Bosons are the force carriers that mediate interactions between particles. The four fundamental forces are electromagnetic force, carried by photons, which governs light, electricity, and magnetism. Weak nuclear force, carried by W and Z bosons, responsible for radioactive decay. Strong nuclear force, carried by gluons, which holds protons and neutrons together inside the atomic nucleus. And gravity, which is not yet fully explained in the Standard Model, but is theorized to be mediated by a hypothetical particle called the graviton. One of the key discoveries in the Standard Model is the Higgs boson, sometimes called the God particle. Discovered in 2012 at the Large Hadron Collider, the Higgs boson explains why particles have mass, which allows the universe to take shape as we know it. Despite its success in describing fundamental interactions, the Standard Model has limitations. It does not include gravity, it does not explain dark matter and dark energy, and it does not fully integrate the force of gravity with quantum mechanics. Scientists continue searching for a theory beyond the Standard Model, such as string theory or quantum gravity, to unify all known forces. The Standard Model remains one of the greatest achievements in modern physics, providing a deep understanding of the universe at its most fundamental level. It allows scientists to predict and test the behavior of particles, leading to technological advancements in computing, medicine, and energy research. Level 52. Quantum Superposition. Quantum superposition is one of the most fundamental and bizarre principles of quantum mechanics. It states that a particle can exist in multiple states or locations at the same time until it is observed or measured. This idea defies classical intuition, where objects exist in only one state at a time. The most famous thought experiment illustrating superposition is Schrödinger's cat. In this scenario, a cat is placed inside a box with a mechanism that has a 50% chance of releasing poison, triggered by the quantum behavior of a particle. Until the box is opened and the cat is observed, it is considered to be both alive and dead at the same time, a paradox that highlights the strange nature of superposition. At a quantum level, particles like electrons and photons exist in a superposition of multiple possible states. For example, an electron orbiting an atom is not in one fixed position, but exists in all possible locations simultaneously until measured. When observed, the superposition collapses into a single, definite state, a process known as wave function collapse. Quantum superposition is not just theoretical, it has real-world applications. It is the foundation of quantum computing, where quantum bits can exist as both 0 and 1 at the same time, unlike classical bits, which can only be either 0 or 1. This ability allows quantum computers to perform complex calculations exponentially faster than traditional computers. Superposition is also crucial in quantum cryptography, quantum teleportation, and emerging technologies. Scientists continue to explore this phenomenon to develop future technologies that could revolutionize computing, communication, and even our understanding of reality itself. Level 53. Quantum Entanglement. Quantum entanglement is one of the most mysterious and fascinating phenomena in quantum mechanics. It occurs when two or more particles become so deeply connected that the state of one instantly affects the state of the other, no matter how far apart they are. This defies classical physics, where information cannot travel faster than the speed of light. Albert Einstein famously called entanglement spooky action at a distance, because it seemed to contradict the laws of relativity. However, experiments have confirmed that when two particles become entangled, Measuring one instantly determines the state of the other, even if they are separated by vast distances. Entanglement works because particles share a combined quantum state, meaning that their properties, such as spin, polarization, or momentum, are linked. If one entangled particle is measured to have spin up, the other must be spin down, regardless of the distance between them. This happens instantaneously, suggesting that information is shared in a way not yet fully understood. This phenomenon has practical applications in emerging technologies. Quantum cryptography uses entanglement to create ultra-secure communication systems, as any attempt to eavesdrop on an entangled message would immediately be detected. Quantum teleportation allows for the instant transfer of quantum information, laying the groundwork for advanced quantum networks. Entanglement also plays a role in the development of quantum computing, where entangled qubits can process information far more efficiently than traditional bits. Scientists are still exploring the deeper implications of entanglement, as it challenges our fundamental understanding of reality and could lead to revolutionary breakthroughs in physics and technology. Level 54, Quantum Tunneling. Quantum tunneling is a phenomenon in quantum mechanics where particles can pass through energy barriers that would be impossible to cross under classical physics. This occurs because, at a quantum level, particles behave as both waves and particles, allowing them to leak through barriers instead of being completely stopped. In classical physics, if a ball is rolling toward a hill without enough energy to climb over it, it will stop. However, in the quantum world, a particle facing a similar barrier has a small probability of tunneling through and appearing on the other side, even without enough energy to overcome the barrier directly. This is possible because of wave function probability, where a particle exists in multiple states until measured. Quantum tunneling is not just theoretical, it has real-world applications. It is essential in nuclear fusion, where atomic nuclei overcome repulsive forces to fuse together, powering the sun and stars. It also enables scanning tunneling microscopes to image surfaces at the atomic level by detecting electrons that tunnel between a sharp probe and a sample. Another major application is in modern electronics. Transistors in microchips and semiconductors rely on quantum tunneling to control electrical flow, making advanced computing possible. Future technologies, including quantum computing, also rely on tunneling effects to perform calculations at unprecedented speeds. Quantum tunneling challenges classical concepts of barriers and limitations, revealing that in the quantum world, particles can do the impossible, shaping the physics of everything from nuclear reactions to the smallest electronic devices. Level 55. Time dilation. Time dilation is a phenomenon predicted by Einstein's theory of relativity, where time moves slower for an object in motion or in a strong gravitational field compared to an observer at rest. This means that time is not absolute, but instead depends on speed and gravity. There are two types of time dilation: velocity-based and gravitational. Velocity-based time dilation. According to Einstein's special theory of relativity, as an object moves closer to the speed of light, time slows down relative to an outside observer. If an astronaut were to travel at near light speeds, they would age more slowly compared to people on Earth. This is known as the twin paradox, where a twin traveling in space returns younger than their sibling who stayed on Earth. Gravitational time dilation. In Einstein's general theory of relativity, time also slows down in the presence of strong gravitational fields. The closer an object is to a massive body, such as a black hole, the slower time moves for it compared to an observer farther away. This has been observed in satellites orbiting Earth, which experience slightly faster time than people on the ground due to weaker gravity. Time dilation has been experimentally confirmed using atomic clocks, which run at different speeds when placed on airplanes, satellites, or at different altitudes. A GPS must correct for time dilation effects to provide accurate positioning data, as the clocks on satellites tick slightly faster than those on Earth. Time dilation challenges our everyday understanding of time, showing that it is not fixed but relative. It plays a crucial role in cosmology, space travel, and high-energy physics, proving that the universe operates far beyond human intuition. Level 56. General Relativity. General relativity is Albert Einstein's revolutionary theory that describes how gravity is not just a force, but the curvature of space-time caused by mass and energy. This theory, published in 1915, replaced Newton's concept of gravity as a simple force and fundamentally changed our understanding of the universe. At its core, general relativity states that massive objects bend space-time, and this curvature tells objects how to move. Imagine space-time as a rubber sheet. If you place a heavy ball on it, the sheet bends. A smaller object rolling nearby will follow the curved path around the larger one. This is how planets orbit stars and how light bends around massive objects like black holes. One of the most famous predictions of general relativity is gravitational time dilation, where time runs slower in stronger gravitational fields. This has been confirmed with atomic clocks placed at different altitudes. Clocks closer to Earth's surface tick slightly slower than those in orbit. Another key effect is gravitational lensing, where light bends around massive objects, making distant galaxies appear distorted or even duplicated. This effect has been used to observe objects billions of light years away and confirm the presence of dark matter. General relativity also predicts gravitational waves, ripples in space-time caused by massive objects like merging black holes. These waves were first detected in 2015 by LIGO, proving one of Einstein's last unconfirmed predictions. General relativity is crucial for modern technology, including GPS systems, satellite communications, and astrophysics. It remains one of the most successful theories in physics, shaping our understanding of black holes, the expansion of the universe, and the fundamental nature of space and time. Level 57. Dark matter. Dark matter is one of the greatest mysteries in modern physics. It is an invisible, unknown substance that makes up about 27% of the universe. Yet it does not emit, absorb, or reflect light, making it completely undetectable by conventional telescopes. Scientists only know it exists because of its gravitational effects on galaxies and galaxy clusters. The concept of dark matter arose when astronomers observed that galaxies rotate much faster than expected. According to Newtonian physics, the outer edges of galaxies should move slower than their dense centers. However, galaxies spin as if they contain far more mass than what is visible, implying the presence of an unseen mass, which we call dark matter. Scientists hypothesize that dark matter consists of yet-to-be-discovered particles, possibly WIMPs, weakly interacting massive particles, or axions, which do not interact with light or electromagnetic forces, but exert gravitational influence. Despite numerous experiments, these particles have not been directly detected. Dark matter also plays a crucial role in gravitational lensing, where its gravity bends light from distant galaxies, distorting their appearance. Observations from cosmic background radiation and galaxy distribution further support the existence of dark matter, as it helps explain the large-scale structure of the universe. Although dark matter remains a mystery, its presence is essential for understanding how galaxies form and how the universe evolved. Scientists continue searching for it using underground detectors, space telescopes, and high-energy particle experiments. Unlocking the secret of dark matter could lead to a deeper understanding of fundamental physics and the true nature of the cosmos. Level 58. Dark energy. Dark energy is the mysterious force causing the universe to expand at an accelerating rate. It makes up about 68% of the universe, yet its nature remains unknown. While dark matter holds galaxies together, dark energy works in the opposite way, pushing the universe apart. The discovery of dark energy came in the late 1990s when astronomers studying supernovae found that distant galaxies were moving away from us faster than expected. Instead of slowing down due to gravity, the expansion of the universe was accelerating. This could only be explained by an unknown energy permeating space, which scientists named dark energy. One explanation for dark energy is Einstein's cosmological constant, a concept he originally introduced in his equations of general relativity. It suggests that empty space itself has energy, and as the universe expands, more space is created, increasing the effect of dark energy over time. Another theory suggests that dark energy is a new, undiscovered force or field, sometimes referred to as quintessence. Dark energy shapes the fate of the universe. If its influence continues to grow, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart. Alternatively, dark energy could weaken, leading to a big crunch where the universe collapses back on itself. Despite its mystery, dark energy is crucial to our understanding of cosmology, gravity, and the universe's evolution. Scientists study it using telescopes, cosmic background radiation, and large-scale galaxy surveys, hoping to unlock one of the greatest unsolved mysteries of modern physics. Level 59. Black holes and event horizons. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse under their own gravity, compressing all their mass into an infinitely dense point called a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. The event horizon is often called the point of no return. Anything crossing this invisible boundary, including light, is trapped forever due to the extreme gravitational pull. The closer an object gets to the event horizon, the more it experiences gravitational time dilation, where time slows down relative to an outside observer. Black holes come in different sizes. Stellar black holes form from dying stars, while supermassive black holes, millions to billions of times the sun's mass, reside at the centers of galaxies, including our own Milky Way. Scientists believe supermassive black holes influence galaxy formation and evolution. Although black holes are invisible, their presence is detected through their effects on surrounding matter. Accretion disks, made of superheated gas spiraling into the black hole, emit powerful X-rays. Black holes can also bend light through gravitational lensing, warping the view of objects behind them. In 2019, the first ever image of a black hole's event horizon was captured by the Event Horizon Telescope, providing direct evidence of their existence. Black holes may also play a role in some of the universe's biggest mysteries, such as wormholes, Hawking radiation, and the nature of space-time itself. Studying them helps physicists explore the limits of general relativity, quantum mechanics, and the true structure of reality. Level 60. Hawking radiation. Hawking radiation is a theoretical process in which black holes slowly lose mass and energy by emitting radiation, eventually causing them to shrink and evaporate over time. This idea was proposed by Stephen Hawking in 1974 and revolutionized our understanding of black holes. According to quantum mechanics, empty space is not truly empty. Instead, it is filled with virtual particle pairs, a particle and its antiparticle, that spontaneously appear and annihilate each other almost instantly. Near the event horizon of a black hole, however, something different can happen. If one of these virtual particles falls into the black hole, while the other escapes, the black hole loses a tiny amount of energy. Over time, this process causes the black hole to slowly radiate energy and shrink. Hawking radiation suggests that black holes are not completely black. They emit faint radiation, primarily in the form of low-energy photons. For massive black holes, this radiation is incredibly weak, meaning they take trillions of years to evaporate. However, small black holes would radiate more rapidly and could evaporate much faster. This discovery was groundbreaking because it connected quantum mechanics, general relativity, and thermodynamics, three fundamental areas of physics that are not yet fully unified. It also led to the famous black hole information paradox, the question of whether information that falls into a black hole is truly lost or somehow preserved in Hawking radiation. Although Hawking radiation has not yet been directly observed, its theoretical basis is widely accepted. Scientists continue to study black holes, hoping to confirm this effect and gain deeper insights into the nature of quantum gravity, space-time, and the ultimate fate of black holes. Level 61. Neutron stars and pulsars. Neutron stars are the collapsed cores of massive stars that have exploded in supernovae. They are among the densest objects in the universe, packing more mass than the Sun into a sphere only about 10 to 20 kilometers wide. A single teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars form when a dying star is too massive to become a white dwarf, but not massive enough to collapse into a black hole. In the explosion, electrons and protons in the star's core combine to form neutrons, leaving behind an incredibly dense, rapidly spinning object with a powerful magnetic field. Some neutron stars emit beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep across space, appearing as pulses of light when observed from Earth. These neutron stars are called pulsars, short for pulsating stars. They can rotate at astonishing speeds, some up to hundreds of times per second, due to the conservation of angular momentum as the star shrinks. Pulsars serve as cosmic lighthouses, and their incredibly precise rotations make them useful for studying gravity, testing Einstein's general relativity, and even aiding spacecraft navigation. In some cases, pulsars exist in binary systems, orbiting another star or even a black hole, offering key insights into extreme physics. Neutron stars also play a role in the creation of heavy elements like gold and platinum. When two neutron stars collide, they release vast amounts of energy and material, forming elements that eventually spread across the cosmos. Studying neutron stars and pulsars helps astronomers explore the limits of matter, gravity, and nuclear physics, providing a glimpse into some of the most extreme environments in the universe. Level 62. Superconductivity. Superconductivity is a quantum phenomenon where certain materials can conduct electricity without any resistance when cooled below a critical temperature. This means that electrical currents in a superconducting material can flow indefinitely without losing energy, making it one of the most important discoveries in condensed matter physics. In a normal conductor, such as copper or silver, electrons move through the material but collide with atoms, creating resistance and losing energy as heat. In a superconductor, however, electrons form Cooper pairs, which move through the material without scattering, eliminating electrical resistance entirely. This occurs because of quantum interactions with the crystal lattice of the material. Superconductors also exhibit the Meissner effect, where they completely expel magnetic fields, allowing them to levitate magnets. This property is being explored for advanced technologies such as magnetic levitation trains, which float above the tracks, reducing friction and enabling ultra-fast transportation. Most superconductors require extremely low temperatures, often close to absolute zero, making their practical use challenging. However, researchers have discovered high-temperature superconductors that work at liquid nitrogen temperatures, making them easier to use in applications like MRI machines and energy-efficient power grids. Scientists continue searching for room-temperature superconductors, which could revolutionize energy transmission, computing, and even quantum technology. If achieved, it would lead to zero-loss power grids, ultra-fast computing, and advanced medical imaging, transforming industries and scientific research. Superconductivity remains one of the most intriguing areas of physics, offering both theoretical challenges and groundbreaking technological potential. Level 63. Nanotechnology. Nanotechnology is the science of manipulating matter at the atomic and molecular scale, typically dealing with structures smaller than 100 nanometers, about 1,000 times thinner than a human hair. At this scale, materials exhibit unique physical, chemical, and biological properties, enabling groundbreaking advancements across multiple industries. At the nanoscale, quantum effects become dominant, and materials can behave in ways that differ from their larger forms. For example, gold nanoparticles change color depending on their size, and carbon nanotubes are stronger than steel, yet lighter than plastic. These properties make nanotechnology essential in fields like medicine, electronics, energy, and materials science. In medicine, nanotechnology is revolutionizing drug delivery, enabling targeted treatments that deliver medicine directly to disease cells, such as in cancer therapy. Nanorobots, or nanobots, are being developed to repair tissues, remove harmful substances, and even perform microscale surgeries inside the body. In electronics, nanotechnology has led to smaller, faster, and more efficient devices. Modern microprocessors contain billions of nanoscale transistors, enabling powerful computing in smartphones, AI systems, and quantum computers. In energy, nanomaterials improve solar cells, batteries, and fuel cells, making them more efficient and sustainable. Nanocoatings are also used to create self-cleaning surfaces, stain-resistant fabrics, and anti-reflective glass. Despite its vast potential, nanotechnology raises ethical and safety concerns, such as the unknown health effects of nanoparticles and the environmental impact of nanomaterials. Scientists are working to ensure responsible development while unlocking nanotechnology's full potential. From medicine to space exploration, nanotechnology is transforming science and industry, offering solutions that were once thought impossible. Its continued advancement will shape the future of materials, medicine, and technology in ways we are only beginning to understand. Level 64, Artificial Intelligence and Deep Learning. Artificial intelligence is the science of creating machines that can perform tasks requiring human intelligence, such as problem-solving, pattern recognition, and decision-making. AI has rapidly advanced due to deep learning, a subset of machine learning that mimics the structure of the human brain using neural networks. At its core, AI relies on algorithms that process large amounts of data, learning from patterns and making predictions. Traditional AI models required explicit programming, but modern deep learning models use neural networks, multi-layered systems that learn from data without human intervention. The more data they process, the better they become. Deep learning has revolutionized fields such as computer vision, natural language processing, and robotics. AI now powers voice assistants like Siri and Alexa, self-driving cars, recommendation systems, and even medical diagnostics. One of the key breakthroughs in AI is the transformer model, which enables AI to process and understand language at unprecedented levels. This has led to real-world applications like real-time language translation, automated customer support, and even AI-assisted scientific research. However, AI comes with challenges and ethical concerns, including bias in training data, misinformation, and the impact on jobs and privacy. There are also concerns about AI safety, as increasingly powerful models raise questions about control and responsibility. As AI continues to evolve, it holds the potential to revolutionize industries, accelerate scientific discoveries, and reshape human interactions with technology. While AI is not yet fully autonomous, its rapid progress suggests a future where it will play an even greater role in shaping society, decision-making, and innovation. Level 65, Quantum Computing. Quantum computing is a revolutionary technology that harnesses the principles of quantum mechanics to process information in ways that classical computers cannot. Unlike traditional computers, which use bits that exist as either 0 or 1, quantum computers use qubits, which can exist in multiple states simultaneously due to superposition and entanglement. These properties allow quantum computers to perform highly complex calculations at speeds exponentially greater than classical machines. Superposition enables qubits to be both 0 and 1 at the same time, significantly increasing computational power. Meanwhile, quantum entanglement links qubits in such a way that changing one instantly affects the other, regardless of distance. These unique characteristics make quantum computing an exciting frontier in science and technology. This technology has the potential to revolutionize multiple industries by solving problems that are currently impossible or impractical for even the most powerful supercomputers. In cryptography, quantum computers could break traditional encryption, but also enable ultra-secure quantum encryption. In drug discovery and material science, they could simulate molecules at the quantum level, leading to breakthroughs in medicine, superconductors, and advanced materials. In artificial intelligence and optimization, quantum algorithms could dramatically improve machine learning, logistics, and financial modeling by solving complex problems exponentially faster than classical methods. Despite its promise, quantum computing is still in its early stages. Qubits are highly sensitive and require extreme cooling near absolute zero to maintain stability and reduce errors. Companies like Google, IBM, and D-Wave are racing to develop scalable, error-corrected quantum systems. In 2019, Google claimed to have achieved quantum supremacy by solving a problem in minutes that would take classical computers thousands of years. As quantum technology continues to advance, it could redefine computing, security, and scientific research, unlocking capabilities far beyond anything possible with today's hardware. Level 66, DNA Nanotechnology. DNA nanotechnology engineers create nanoscale structures and devices using DNA molecules as programmable building blocks. Unlike traditional nanotechnology, which relies on metals or synthetic materials, this approach leverages DNA's self-assembling properties to create precise molecular designs. Base pairing allows adenine to bind with thymine and cytosine with guanine, enabling scientists to construct custom DNA structures from simple geometric shapes to dynamic molecular machines. A major breakthrough in this field is DNA origami, where long DNA strands fold into intricate 2- and 3-dimensional structures that function as molecular scaffolds, drug carriers, or nanoscale robotic devices. In medicine, DNA nanostructures enable targeted drug delivery, transporting treatments directly to disease cells while minimizing side effects. DNA-based biosensors detect toxins, viruses, and biological changes, improving diagnostics. In technology, nanoelectronics uses DNA to assemble ultra-small circuits, advancing computing. Synthetic biology expands DNA nanotechnology into biological computation, programming molecular systems to perform logical operations inside living cells. Challenges remain, including stability in biological environments and large-scale production, but advances in CRISPR, synthetic biology, and molecular engineering continue to refine these techniques. This fusion of biology, chemistry, and engineering could revolutionize precision medicine, molecular robotics, and next-generation materials. As research progresses, DNA nanotechnology may redefine how scientists build and program matter at the nanoscale, unlocking new possibilities across multiple fields. Level 67. Terraforming. Terraforming is the hypothetical process of modifying a planet's environment to make it habitable for humans by altering its atmosphere, temperature, and ecology. Though currently beyond our technological capabilities, scientists have explored it as a way to expand civilization beyond Earth. Mars is the most discussed candidate due to its thin atmosphere, extreme cold, and lack of surface water. Proposed methods include releasing greenhouse gases from polar ice caps to warm the planet, redirecting ammonia-rich asteroids to introduce gases, and using space mirrors to reflect more sunlight. Another approach involves genetically engineered microbes to produce oxygen and improve soil for plant life. Terraforming Venus presents the opposite challenge. Its dense, toxic atmosphere and extreme heat would require cooling, removing carbon dioxide, and introducing reflective materials to reduce heat absorption. This process poses immense challenges, requiring advanced technology, vast resources, and centuries of effort. Ethical concerns arise over modifying planets, especially if microbial life exists there. Even if successful, ongoing maintenance would be needed to prevent a planet from reverting to its original state. Despite these obstacles, studying terraforming advances planetary science, climate engineering, and space exploration. While large-scale planetary transformation may be far off, This research helps us understand atmospheric processes, climate change, and the future of sustaining life beyond Earth. If humanity expands into space, terraforming could be key to long-term survival on other worlds. Level 68. Dyson Spheres. A Dyson sphere is a hypothetical megastructure designed to surround a star and capture its energy, providing an advanced civilization with virtually unlimited power. Proposed by physicist Freeman Dyson in 1960, the concept is based on the idea that as a civilization grows, its energy demands will surpass what a single planet can provide. To sustain its expansion, a highly developed society, classified as a Type 2 civilization on the Kardashev scale, would need to harness the full energy output of its star, making a Dyson sphere a potential solution. Several variations of this concept have been proposed. A Dyson swarm consists of a vast network of orbiting solar satellites, each capturing energy and transmitting it back to the civilization. This is considered the most feasible version. A Dyson ring, a simpler structure forming a partial loop around the star, has been popularized in science fiction. The most extreme version, a Dyson shell, would be a completely enclosed sphere surrounding the star, though this is considered structurally unstable due to immense gravitational forces. If Dyson spheres exist elsewhere in the universe, they could be detectable by observing stars with unusual infrared heat signatures, as any large-scale energy-collecting structure would re-emit excess energy as heat. Scientists at SETI search for extraterrestrial intelligence, scan the cosmos for such signals, hoping they might indicate the presence of an advanced alien civilization. Although no Dyson sphere has been discovered, the concept remains influential in space engineering, energy collection, and megastructure design. If humanity ever constructs such a structure, it would mark a profound step toward interstellar expansion, the creation of artificial habitats, and possibly even terraforming other planets. While currently beyond technological reach, the study of Dyson spheres continues to inspire scientists and engineers to explore the possibilities of harnessing the full power of a star, a milestone that could reshape the future of civilization. Level 69. Extraterrestrial Life and Astrobiology. Extraterrestrial life is one of the biggest unanswered questions in science. Astrobiology explores the possibility of life beyond Earth by studying extreme environments, planetary conditions, and biosignatures. Scientists believe that life, as we know it, requires liquid water, a stable atmosphere, and essential chemical elements, but alien life could be vastly different. The search for life focuses on exoplanets in the habitable zone, where conditions might allow water to exist. Moons like Europa and Enceladus have subsurface oceans, making them prime candidates for microbial life. Mars may have hosted life in the past, and missions like Perseverance are searching for evidence. Scientists also analyze exoplanet atmospheres for chemical signs of life, such as oxygen or methane, using advanced telescopes. The SETI program scans the cosmos for artificial signals, hoping to detect intelligent civilizations. Studying extremophiles on Earth, organisms that thrive in extreme heat, acidity, or radiation, helps us understand how alien life might survive in harsh environments. If extraterrestrial life is found, it would change our understanding of biology, evolution, and our place in the universe. Whether it's simple microbes on a distant moon or advanced civilizations light years away, the discovery would be one of the most profound moments in human history. Until then, the search continues. Level 70. String Theory. String theory is a bold attempt to unify all of physics under a single framework. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. The way these strings vibrate determines the properties of particles, such as their mass, charge, and force interactions. If true, string theory could bridge the gap between quantum mechanics and general relativity, solving one of the biggest challenges in modern physics. For string theory to work, it requires the existence of extra dimensions beyond the familiar three of space and one of time. Instead of 4 dimensions, the universe might have 10 or 11, with the extra ones being too small to detect. These hidden dimensions allow for the mathematical consistency needed to describe all fundamental forces, including gravity, as different vibrational patterns of strings. One major outcome of string theory is M-theory, which suggests that strings may also exist as higher dimensional objects called branes. Some interpretations even propose that our universe could be a 3-dimensional brane floating in a higher dimensional space, possibly interacting with other branes or parallel universes. Despite its elegance, string theory remains untested, as its predictions occur at energy levels far beyond current experiments. Unlike other theories in physics, which have been confirmed through observations, string theory has yet to provide testable evidence. However, advancements in particle physics, black hole studies, and cosmology may one day provide clues that validate or disprove its ideas. If string theory is correct, it would be the theory of everything, unifying all known forces and particles under one fundamental framework. It could explain the deepest mysteries of the universe, from the smallest quantum particles to the nature of space-time itself. Whether it turns out to be the ultimate solution or just a stepping stone to a deeper theory, string theory continues to inspire physicists in their quest to understand the true nature of reality. Level 71, the Multiverse Hypothesis. The multiverse hypothesis suggests that our universe is just one of many, each with its own unique laws of physics, space, and time. If true, this would mean reality is far larger and more complex than we ever imagined. The idea comes from multiple areas of physics, including quantum mechanics, cosmology, and string theory. One version of the multiverse comes from quantum mechanics. The many worlds interpretation proposes that every time a quantum event has multiple possible outcomes, the universe splits, creating parallel realities where each possibility plays out. This means there could be an infinite number of versions of you, each living a slightly different life. Another possibility arises from cosmic inflation, which suggests that during the rapid expansion of the early universe, other bubble universes could have formed. These universes may have different physical constants, leading to entirely different laws of physics, some allowing life and others not. String theory also introduces the idea of multiple dimensions and brane worlds, where our universe could be just one of many floating in a higher dimensional space. While the multiverse is a fascinating idea, there is currently no direct evidence to prove it. Some scientists look for subtle imprints in cosmic background radiation or anomalies in quantum experiments that might hint at interactions with other universes. If proven, the multiverse would redefine our understanding of existence, suggesting that everything that can possibly happen does happen somewhere in another universe. Level 72, Cosmic Inflation. Cosmic inflation is the theory that, in the first fraction of a second after the Big Bang, the universe expanded exponentially, growing from a microscopic size to nearly its current observable scale. This rapid expansion helps explain several mysteries in cosmology, including why the universe appears so smooth, uniform, and flat on large scales. Before inflation was proposed, scientists struggled to explain why regions of the universe that are billions of light years apart have nearly the same temperature and density, even though they should not have had enough time to exchange information. Inflation solves this by suggesting that all parts of the universe were once in close contact, then expanded so quickly that they retained similar properties. It also explains why the universe appears flat rather than curved, as inflation would have stretched space so much that any initial curvature became negligible. Proposed by physicist Alan Guth in the 1980s, inflation predicts that tiny quantum fluctuations during the rapid expansion were stretched across the universe, eventually forming the galaxies and cosmic structures we see today. These predictions match observations of the cosmic microwave background radiation, the afterglow of the Big Bang, which shows subtle variations that align with inflationary models. Although inflation is widely accepted, the exact mechanism behind it remains unknown. Scientists continue to search for gravitational waves or other signatures that could provide definitive proof. If confirmed, cosmic inflation would offer deep insights into the early universe, the origins of structure, and possibly even the nature of the multiverse itself. Level 73. Panspermia. Panspermia is the hypothesis that life on Earth may have originated from space rather than forming entirely on our planet. It suggests that microbial life, or the building blocks of life, could have traveled between planets, moons, or even star systems, carried by asteroids, comets, or cosmic dust. There are different types of panspermia. Lithopanspermia proposes that life could have been transported between planets within the same solar system, such as from Mars to Earth via meteorites. Radiopanspermia suggests that microscopic life could travel on interstellar dust, pushed by radiation pressure. Directed panspermia, a more speculative idea, proposes that an advanced civilization may have intentionally spread life throughout the universe. Evidence supporting panspermia includes the discovery of organic molecules in meteorites and space dust, as well as the resilience of certain microbes. Some bacteria and extremophiles can survive the vacuum of space, intense radiation, and extreme temperatures, suggesting that life could endure interplanetary journeys. The discovery of amino acids on asteroids and water on Mars further supports the idea that life's ingredients exist beyond Earth. While panspermia does not explain the ultimate origin of life, it raises the possibility that life is widespread in the universe. If life did not begin on Earth but was seeded from elsewhere, it could mean that life exists, or once existed, on Mars, Europa, or other habitable worlds. Future missions searching for biological traces on asteroids, Mars, or icy moons could provide clues to whether panspermia played a role in Earth's history. Level 74. EPR Paradox and Non-Locality. The EPR paradox, named after Einstein, Podolsky, and Rosen, is a thought experiment that challenges the foundations of quantum mechanics, particularly the idea of non-locality. In 1935, Einstein and his colleagues proposed the paradox to argue that quantum mechanics must be incomplete because it allows for instantaneous interactions between distant particles, seemingly violating relativity's speed limit on information transfer. The paradox is based on quantum entanglement, where two particles become linked in such a way that measuring one instantly determines the state of the other, regardless of distance. Einstein famously dismissed this as spooky action at a distance, believing that hidden variables must exist to explain the correlation without violating locality. However, in the 1960s, physicist John Bell developed Bell's theorem, which provided a way to test whether hidden variables could account for quantum correlations. Experiments confirmed that entangled particles exhibit non-local correlations, meaning quantum mechanics cannot be explained by any local hidden variable theory. Non-locality challenges our classical understanding of space and time. While quantum entanglement does not allow faster-than-light communication, it suggests that information about a system is not confined to a single point in space, redefining the nature of reality itself. The implications of the EPR paradox extend to quantum computing, cryptography, and fundamental physics, showing that quantum mechanics is far stranger than Einstein had hoped. Level 75. Quantum gravity. Quantum gravity is the theoretical framework that seeks to unify quantum mechanics and general relativity, two of the most successful but conflicting theories in physics. While quantum mechanics governs the behavior of the smallest particles, and general relativity explains gravity on cosmic scales, these theories break down when applied to extreme conditions, such as inside black holes or at the moment of the Big Bang. A theory of quantum gravity would bridge this gap, providing a deeper understanding of spacetime itself. One of the leading candidates for quantum gravity is string theory, which suggests that particles are not point-like, but instead tiny vibrating strings, with gravity emerging naturally from their interactions. Another approach is loop quantum gravity, which proposes that spacetime itself is quantized, made up of tiny, discrete loops rather than being continuous. Other models, such as the holographic principle, suggest that all the information in the universe may actually be encoded on a lower dimensional boundary. A major challenge in developing quantum gravity is the lack of experimental evidence. Unlike quantum mechanics or relativity, which have been tested extensively, quantum gravity operates at energy scales far beyond current technology. However, indirect evidence may come from studying gravitational waves, black holes, or the cosmic microwave background, where traces of quantum gravitational effects might be detected. If a successful theory of quantum gravity is discovered, it could revolutionize our understanding of the universe, explaining the true nature of space-time, the behavior of singularities, and possibly even what happened before the Big Bang. It remains one of the greatest unsolved mysteries in physics, but unlocking it could reshape our fundamental view of reality. Level 76. Loop quantum gravity. This is a theoretical approach to quantum gravity that suggests space-time itself is made up of tiny, discrete loops, rather than being a continuous fabric. This idea challenges our traditional view of space and time, proposing that at the smallest scales, the universe is fundamentally granular. Unlike string theory, which describes particles as vibrating strings in extra dimensions, loop quantum gravity takes a different approach by applying quantum mechanics directly to Einstein's general relativity. In this framework, space-time is composed of a network of interconnected loops, forming a dynamic, ever-changing structure. These loops are thought to be at the Planck scale, an unimaginably small length where quantum gravitational effects become dominant. One of the most fascinating predictions of loop quantum gravity is that it eliminates singularities, such as the infinite density found at the center of black holes or the beginning of the Big Bang. Instead of a singularity, loop quantum gravity suggests that space-time undergoes a quantum bounce, meaning the universe may have existed before the Big Bang, contracting and then expanding again in an endless cycle. Although loop quantum gravity remains untested, physicists are searching for indirect evidence through gravitational wave observations, black hole physics, and high-energy cosmic phenomena. If proven, it would offer a radical new picture of the universe, revealing that space-time itself has a quantum structure, and possibly leading to a deeper understanding of the fundamental nature of reality. Level 77. Topological quantum computing. Topological quantum computing is a cutting-edge approach to building quantum computers that relies on exotic quantum states known as anyons, which exist in certain two-dimensional systems. Unlike standard quantum bits that are easily disturbed by environmental noise, topological qubits are much more stable, making them a promising solution for fault-tolerant quantum computing. In classical computing, bits store information as zeros and ones, while quantum computing uses qubits, which can exist in a superposition of both states. However, most quantum computing methods struggle with decoherence, where qubits lose their quantum state due to external disturbances. Topological quantum computing avoids this issue by encoding information in braided quantum states, where quantum information is stored in the way anyons move and intertwine rather than their specific quantum state. Anyons obey unique non-abelian statistics, meaning that when they are braided around each other, they store quantum information in a way that is resistant to local errors. This topological protection makes computations more robust against noise, offering a major advantage over other quantum computing approaches. While still in early stages, researchers, including those at Microsoft and other institutions, are working on implementing topological qubits using materials like Majorana fermions, which could revolutionize quantum computing by significantly improving error correction. If successful, topological quantum computing could lead to scalable, stable, and ultra-powerful quantum processors, accelerating breakthroughs in fields such as cryptography, materials science, and artificial intelligence. Level 78. Chiral superconductivity. This is a special type of superconductivity where electrons pair and flow in a preferred asymmetrical direction, breaking conventional symmetry in the material. Unlike standard superconductors, where electron pairs move without resistance in all directions, chiral superconductors exhibit a kind of built-in handedness, meaning their electron pairs circulate in a specific rotational pattern, similar to how water swirls in a vortex. This unique behavior is linked to topology and quantum mechanics, making chiral superconductors potentially useful for advanced technologies, including topological quantum computing and next-generation electronic devices. The chiral nature of these materials allows them to host Majorana fermions, exotic particles that could serve as the foundation for fault-tolerant quantum computing. Scientists believe that certain unconventional superconductors, such as strontium rufinate, may exhibit chiral superconductivity, though definitive experimental confirmation remains a challenge. If discovered and fully understood, chiral superconductors could revolutionize how we manipulate quantum information, leading to breakthroughs in quantum materials, low-energy electronics, and fundamental physics. Level 79. Quantum Sensors. Quantum sensors are devices that use the principles of quantum mechanics to measure physical properties with unprecedented precision. Unlike classical sensors, which rely on conventional physics, quantum sensors exploit superposition, entanglement, and quantum coherence to detect even the tiniest changes in gravity, magnetic fields, time, and motion. One of the most promising quantum sensing technologies is based on atomic interferometry, where the wave-like nature of atoms is used to measure acceleration and gravitational forces with extreme accuracy. This has applications in navigation systems, geophysics, and detecting underground structures without relying on GPS. Another key area is magnetometry, where quantum sensors based on nitrogen vacancy centers in diamonds can detect magnetic fields at the nanoscale. These sensors are used in medical imaging, brain activity monitoring, and detecting hidden explosives or materials. Quantum sensors are also revolutionizing timekeeping, with atomic clocks now so precise that they lose only a fraction of a second over billions of years. These advancements improve GPS, financial trading, and space exploration. As quantum technology advances, quantum sensors are expected to play a crucial role in earth science, healthcare, military defense, and fundamental physics research. Their ability to detect the smallest disturbances could even help in the search for dark matter and gravitational waves, opening new frontiers in our understanding of the universe. Level 80. Brain-computer interfaces and neural prosthetics. BCIs and neural prosthetics are technologies that connect the human brain directly to external devices, allowing for communication, control, and even sensory restoration. These systems translate neural signals into digital commands, enabling people to operate computers, robotic limbs, or medical implants using only their thoughts. BCIs work by detecting electrical activity in the brain, often using electrodes placed on or inside the skull. These signals are processed by machine learning algorithms to interpret a person's intentions. Neural prosthetics use similar technology to restore lost functions, such as enabling paralyzed individuals to control robotic limbs or allowing cochlear implants to restore hearing. Recent breakthroughs include brain implants that allow speech synthesis, restoring communication for people with severe disabilities. Research into BCI-assisted memory enhancement and neural implants for treating neurological disorders is also advancing rapidly. Companies like Neuralink are working toward high-bandwidth brain interfaces that could one day merge human cognition with artificial intelligence. While BCIs offer incredible potential, challenges remain, including long-term safety, ethical concerns, and privacy risks. However, as technology improves, brain-computer interfaces could revolutionize medicine, communication, and human-machine interaction, blurring the line between biology and technology. Level 81. Von Neumann probes. Von Neumann probes are theoretical, self-replicating spacecrafts designed to explore the universe autonomously. Named after mathematician John von Neumann, who pioneered the concept of self-replicating machines, these probes would use raw materials from asteroids, moons, or planets to construct copies of themselves, allowing for exponential exploration across the galaxy. Unlike traditional spacecraft, which require human intervention or fuel resupply, von Neumann probes would be fully autonomous, equipped with AI, robotics, and advanced manufacturing systems. After arriving at a target system, they would scan for resources extract materials, and build new probes, which would then continue the process, creating an expanding wave of exploration. This method could enable a civilization to map the galaxy in a fraction of the time required by conventional missions. If such probes exist, they could already be traveling through space or even present in our own solar system. The Fermi paradox, which questions why we have not detected alien civilizations despite the vast number of habitable planets, suggests that if extraterrestrials have developed von Neumann probes, they should be widespread. Some theorists speculate that advanced civilizations may have placed restrictions on self-replicating probes, fearing unintended consequences like runaway replication or competition between different species probes. Despite being theoretical, the concept of self-replicating spacecraft has profound implications for space exploration, interstellar colonization, and the search for extraterrestrial intelligence. If humanity ever constructs von Neumann probes, they could become the ultimate tool for reaching distant star systems, paving the way for automated resource extraction, planetary engineering, and even first contact with alien civilizations. Level 82. Matryoshka Brains. A Matryoshka brain is a hypothetical megascale computational structure that surrounds a star, harnessing its energy to power an advanced superintelligence. The concept builds upon the Dyson sphere, but instead of simply collecting energy, a Matryoshka brain would use that energy to fuel an immense layered network of computational devices, allowing for near unimaginable levels of processing power. The structure is named after Matryoshka dolls, the nested Russian dolls, because it consists of multiple concentric shells of computing systems, each absorbing energy from the layers beneath it. The innermost layer would be closest to the star, directly converting its radiation into computation, while outer layers recycle waste heat, ensuring maximum energy efficiency. This would allow a civilization to utilize almost 100% of a star's output, achieving a Type 2 or 3 civilization on the Kardashev scale. A Matryoshka brain could serve as a galactic-scale AI, simulating entire universes, storing vast amounts of consciousness, or even running detailed simulations of reality itself. It could be used for purposes ranging from engineering and research to creating digital utopias where post-biological beings exist in a purely virtual world. While entirely speculative, the idea raises deep questions about the limits of intelligence, energy use, and the long-term future of civilizations. If extraterrestrial superintelligences exist, they might not build spaceships. We might instead detect them as giant computational megastructures, absorbing the energy of entire stars. If humanity ever reaches such an advanced level, a Matryoshka brain could represent the ultimate evolution of intelligence, transforming not just a planet, but entire solar systems into vast centers of thought and simulation. Level 83. Exotic matter. Exotic matter refers to forms of matter that do not behave according to the known laws of physics. Unlike ordinary matter, which is made of protons, neutrons, and electrons, exotic matter can have unusual properties such as negative mass, negative energy, or the ability to resist gravitational collapse. Though largely theoretical, exotic matter plays a crucial role in speculative physics, including concepts like wormholes, warp drives, and dark energy. One of the most intriguing types of exotic matter is negative mass, a hypothetical substance where, if pushed, it would accelerate in the opposite direction of the force applied. This behavior defies Newton's laws and could potentially be used to create a warp drive, allowing faster-than-light travel by bending space-time. Another form, Casimir effect vacuum energy, arises in quantum field theory, where quantum fluctuations create small amounts of negative energy between closely spaced plates. Some physicists believe that similar effects could help stabilize traversable wormholes, theoretical tunnels through space-time that could allow near instantaneous travel between distant locations. Exotic matter may also be linked to dark matter and dark energy, the mysterious components that make up most of the universe's mass energy, but remain undetected. Some theories suggest that exotic particles yet to be discovered could be responsible for these unexplained cosmic forces. Although no confirmed examples of exotic matter exist, experiments in quantum physics and high-energy particle accelerators continue to explore its possible existence. If discovered, exotic matter could redefine our understanding of gravity, space-time, and the fundamental structure of reality, potentially unlocking technologies once thought impossible. Level 84, Exotic Propulsion Physics. Exotic propulsion physics explores advanced propulsion systems that go beyond conventional rocketry, potentially enabling faster-than-light travel, interstellar exploration, and manipulation of space-time itself. These propulsion concepts often rely on speculative physics such as negative energy, exotic matter, and quantum field effects, challenging our current understanding of the universe. One of the most well-known ideas is the Alcubierre warp drive, which proposes using a warp bubble to contract space in front of a spacecraft and expand it behind, allowing faster-than-light travel without violating Einstein's relativity. This concept relies on negative energy, a form of exotic matter that has not yet been discovered but is theoretically possible through quantum fluctuations. Another theoretical propulsion system is wormhole travel, where a spacecraft could pass through a shortcut in space-time, instantly reaching distant galaxies. However, to stabilize a traversable wormhole, exotic matter would be needed to prevent it from collapsing. Similarly, quantum vacuum propulsion, which aims to extract energy from quantum fluctuations, could provide a near-limitless energy source for deep space travel. More near-term exotic propulsion concepts include ion drives, nuclear fusion propulsion, and antimatter rockets, all of which could significantly cut travel times within our solar system. Theoretical studies also explore using light sails propelled by laser beams to accelerate spacecraft to a fraction of the speed of light, potentially enabling interstellar missions. While exotic propulsion remains speculative, breakthroughs in quantum mechanics, relativity, and high-energy physics could one day make these technologies a reality. If achieved, exotic propulsion could fundamentally change space exploration, allowing humanity to travel beyond our solar system, explore exoplanets, and even reach distant galaxies, making the dream of interstellar civilization possible. Level 85, Quantum Consciousness. Quantum consciousness theories propose that the mind and consciousness arise from quantum processes occurring within the brain, rather than being purely the result of classical neural activity. These ideas challenge conventional neuroscience by suggesting that quantum mechanics, the strange rules governing subatomic particles, plays a fundamental role in thought, perception, and even free will. One of the most well-known quantum consciousness models is the orchestrated objective reduction theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. This theory suggests that consciousness emerges from quantum superpositions inside microtubules, tiny structures within neurons. According to this theory, when these quantum states collapse, they generate conscious experience, making the brain more than just a classical biological computer. Other theories explore whether quantum entanglement or coherence could enable brain cells to process information in ways that classical physics cannot explain. Some researchers speculate that quantum effects might help explain phenomena such as intuition, creativity, or even near-death experiences, while others question whether quantum mechanics could provide insights into the nature of free will or the hard problem of consciousness, how subjective experience arises from physical matter. However, mainstream neuroscience remains skeptical, as the brain's warm and wet environment is generally thought to destroy quantum coherence too quickly for quantum processes to play a major role in thought. Critics argue that consciousness can be fully explained through classical neural networks and information processing without requiring quantum mechanics. Despite the controversy, quantum consciousness theories continue to inspire research in physics, neuroscience, and philosophy. If quantum effects are proven to play a role in cognition, it could revolutionize our understanding of the mind, bridging the gap between physics and consciousness, and potentially revealing a deeper connection between thought and the fundamental nature of reality. Level 86, ADS-CFT Correspondence. The ADS-CFT correspondence is a groundbreaking concept in theoretical physics that establishes a duality between gravity in a higher dimensional space and a quantum field theory in a lower dimensional space. First proposed by physicist Juan Maldacena in 1997, this idea suggests that a universe governed by gravity in an anti-de Sitter space is mathematically equivalent to a conformal field theory on its boundary. This means that the seemingly different worlds of quantum mechanics and general relativity might actually describe the same underlying reality. In ADS space, which has a constant negative curvature, gravity operates as expected in a higher dimensional setting. However, the boundary of this space, described by CFT, follows the principles of quantum field theory, which governs subatomic particles and their interactions. The key insight of ADS-CFT is that every event inside the gravitational space has a corresponding event in the lower dimensional quantum theory, providing a new way to study black holes, string theory, and even the fundamental nature of space-time itself. One of the most exciting implications of this correspondence is its potential to help solve the black hole information paradox, a major conflict between quantum mechanics and relativity. ADS-CFT also provides insights into strongly interacting quantum systems, such as quark-gluon plasmas created in particle colliders, and may even offer a path toward understanding quantum gravity. Although ADS space does not describe our real universe, since we exist in a de Sitter-like space-time with positive curvature, the mathematical principles behind ADS-CFT have influenced fields ranging from holography to condensed matter physics. This correspondence remains one of the most powerful tools in modern theoretical physics, offering a glimpse into how gravity and quantum mechanics might finally be unified. Level 87, the ekpyrotic universe. The ekpyrotic universe is an alternative to the Big Bang theory, proposing that the universe was not born from a singular explosion, but rather from the collision of two higher dimensional branes in a larger cosmic space. This theory comes from string theory and M theory, offering a radically different explanation for the origins of the cosmos. Unlike the traditional Big Bang model, which suggests the universe began from an infinitely small and hot singularity, the ekpyrotic model suggests that our universe existed before its expansion. In this view, two vast three-dimensional branes, separated in a higher dimensional space, slowly move toward each other. When they collided, their energy was converted into the hot, dense state that led to the universe we observe today. This process explains why the cosmic microwave background radiation appears so uniform, solving key problems that the Big Bang theory struggles with. The ekpyrotic model also suggests that the universe may undergo cyclic events, where brane collisions happen repeatedly over trillions of years, meaning the universe could have existed long before what we perceive as the beginning. This avoids the need for a singularity and offers a more continuous, eternal cosmic timeline. While the ekpyrotic universe remains a speculative idea, it provides a fresh perspective on fundamental questions about time, space, and the nature of cosmic origins. Future advancements in cosmology and high-energy physics could determine whether our universe was truly shaped by a fiery explosion or by the grand cosmic dance of colliding dimensions. Level 88, the ultimate fate of the universe. The ultimate fate of the universe is one of the biggest unanswered questions in cosmology. While the universe is currently expanding due to dark energy, scientists debate what will happen in the far future. The answer depends on factors like the rate of expansion, the density of matter, and the behavior of dark energy. One possibility is the Big Freeze, or heat death, where the universe continues expanding indefinitely. Over time, galaxies drift apart, stars burn out, and even black holes evaporate. Eventually, only a cold, dark void remains, with all energy evenly spread out, making further motion or activity impossible. Another scenario is the Big Crunch, where expansion reverses and gravity pulls everything back together. The universe would shrink, growing hotter and denser until it collapses into a singularity, possibly leading to another Big Bang in a cyclic process. However, current observations suggest the universe's expansion is accelerating, making this less likely. A third idea, the Big Rip, suggests that dark energy might continue growing stronger, tearing apart galaxies, stars, planets, and eventually atoms themselves. In this scenario, even space-time itself is torn apart in a final catastrophic event. Other possibilities include the cosmic bounce, where the universe collapses and then re-expands, or the vacuum decay hypothesis, in which a quantum event destabilizes the universe, creating a lower energy state that expands at the speed of light, erasing everything in an instant. While the ultimate fate of the universe remains uncertain, each theory provides insight into the fundamental forces shaping reality. Whether the cosmos ends in a freeze, a crunch, or something stranger, understanding its fate helps us unravel the deep mysteries of existence. Level 89. Artificial General Intelligence. Artificial General Intelligence, or AGI, refers to a hypothetical form of AI that can perform any intellectual task that a human can, including reasoning, learning, problem-solving, and adapting to new situations without specific programming. Unlike narrow AI, which is designed for specific tasks like voice recognition or playing chess, AGI would possess human-like cognitive abilities, allowing it to think, plan, and make decisions across a broad range of domains. To achieve AGI, machines would need to develop self-learning capabilities, understand abstract concepts, and exhibit common-sense reasoning, something current AI systems lack. Scientists explore different approaches, including neural networks, reinforcement learning, and brain-inspired computing, to build AI that can generalize knowledge the way humans do. If AGI becomes a reality, it could revolutionize society, automating not just routine tasks, but also scientific research, creative work, and decision-making. It could help solve complex global challenges, from climate change to medical breakthroughs. However, AGI also raises profound ethical and existential concerns. If an AGI surpasses human intelligence, it could operate beyond human control, leading to unpredictable consequences. Issues like alignment, safety, and control are critical, as an unregulated AGI could act in ways that are not aligned with human values. While AGI remains theoretical, rapid advancements in machine learning, cognitive computing, and neuroscience-inspired AI suggest that we may one day create machines with true general intelligence. Whether AGI becomes humanity's greatest tool or an existential risk will depend on how it is developed and controlled. Level 90. Quantum Artificial Intelligence. Quantum Artificial Intelligence, QAI, is the fusion of quantum computing and machine learning, aiming to create AI systems that surpass the capabilities of classical computing. By harnessing the principles of superposition, entanglement, and quantum parallelism, QAI could process vast amounts of data and solve problems exponentially faster than traditional AI. In classical AI, algorithms rely on binary computation, where bits represent either 0 or 1. Quantum AI, however, utilizes qubits, which can exist in multiple states simultaneously, enabling the exploration of multiple solutions at once. Quantum entanglement further enhances computation by linking qubits in a way that allows them to share information instantly, improving efficiency in pattern recognition, optimization, and decision-making. Despite its potential, QAI remains in its early stages. Quantum computers are still highly sensitive, requiring near absolute zero temperatures to maintain qubit stability. Additionally, quantum machine learning algorithms are still being developed, with researchers working to overcome error rates and scalability issues. Level 91. Non-Abelian anyons and topological quantum computing. Non-Abelian anyons are exotic quantum particles that obey unique braid statistics, making them key to the development of topological quantum computing. Unlike fermions and bosons, which follow traditional quantum mechanics rules, anyons emerge in two-dimensional systems and exhibit behavior where their quantum state depends on the order in which they are exchanged. This property allows them to store and process quantum information in a way that is highly resistant to errors. In topological quantum computing, information is encoded in the braiding patterns of non-abelian anyons, meaning their states are not easily disturbed by small environmental fluctuations. This built-in error protection makes them far more stable than traditional qubits, which are extremely sensitive to decoherence. Instead of relying on delicate quantum superpositions, these anyons store information in non-local entanglements, which significantly reduces the likelihood of computation errors. One of the most promising candidates for realizing non-abelian anyons is the Majorana fermion, a theoretical particle predicted to exist in certain superconducting materials. Companies like Microsoft are actively researching ways to use these particles to develop scalable and fault-tolerant quantum computers. If successfully implemented, topological quantum computing could revolutionize fields like cryptography, complex simulations, and artificial intelligence by solving problems exponentially faster than classical computers. While challenges remain in experimentally confirming and manipulating non-abelian anyons, their potential to unlock practical, large-scale quantum computing makes them one of the most exciting frontiers in physics and computation. Level 92. Causal Set Theory. Causal set theory is a radical approach to quantum gravity that suggests space-time is not continuous, but fundamentally discrete, made up of indivisible building blocks, much like pixels on a screen. Unlike classical general relativity, which treats space-time as a smooth fabric, causal set theory proposes that at the smallest scales, reality consists of discrete elements connected in a network of causal relationships. This theory addresses a key issue in modern physics, the incompatibility between quantum mechanics and general relativity. If space-time is continuous, applying quantum principles leads to singularities, such as those found in black holes and the Big Bang. By modeling space-time as a causal set, a collection of discrete points ordered by cause and effect relationships, this framework eliminates singularities and provides a more fundamental description of reality. A major implication of causal set theory is that space-time has a smallest possible unit of length, known as the Planck scale, meaning there is no infinitely smooth structure at microscopic levels. This could explain why attempts to unify gravity and quantum mechanics have struggled under traditional continuous models. Additionally, causal set theory naturally accounts for the expansion of the universe, suggesting that new elements of space-time are constantly being added, rather than space stretching as in standard cosmology. Although still theoretical, causal set theory offers a promising direction for quantum gravity research. Experimental tests remain challenging due to the minuscule scales involved, but physicists are exploring ways to detect evidence of discreteness in spacetime through cosmic background radiation, black hole physics, and particle interactions. If proven correct, this theory could fundamentally reshape our understanding of time, space, and the true fabric of the universe. Level 93. Quantum Chromodynamics. Quantum chromodynamics, QCD, is the fundamental theory describing the strong interaction, one of the four fundamental forces of nature. The strong force binds quarks together to form protons, neutrons, and other particles, holding the atomic nucleus together despite the intense repulsion between positively charged protons. Without QCD, atoms, and therefore all matter, would not exist. At the heart of QCD is the concept of color charge, a property similar to electric charge but with three types: red, green, and blue. Quarks interact by exchanging gluons, the force carriers of the strong interaction. Unlike photons in electromagnetism, gluons themselves carry color charge, allowing them to interact with each other in complex ways, making the strong force vastly different from other fundamental forces. One of QCD's most striking features is asymptotic freedom, which means that quarks behave almost as free particles when they are extremely close together. However, as they move apart, the force between them grows stronger, leading to quark confinement, a phenomenon where isolated quarks can never be observed directly. Instead, quarks always combine into bound states, such as protons and neutrons, or mesons, at extreme temperatures and densities, such as those in the early universe or inside neutron stars. QCD predicts the existence of quark-gluon plasma, a state of matter where quarks and gluons are no longer confined but move freely. Experiments at the Large Hadron Collider and Relativistic Heavy Ion Collider have provided evidence for this phase, giving insights into the conditions moments after the Big Bang. Quantum chromodynamics remains one of the most mathematically complex yet experimentally confirmed theories in modern physics. Understanding the strong interaction not only explains the stability of matter, but also unlocks deeper insights into nuclear physics, neutron stars, and the early universe, making QCD a cornerstone of particle physics. Level 94, Geometrodynamics and Space-Time Engineering. Geometrodynamics is a theoretical framework that describes gravity as the dynamic curvature of space-time, rather than as a force in the traditional sense. Proposed by physicist John Archibald Wheeler, it extends Einstein's general relativity, emphasizing that space-time itself is a flexible, evolving entity that can be manipulated under the right conditions. This concept has profound implications for space-time engineering, where advanced civilizations or future human technologies could potentially control or reshape the fabric of the universe. In geometrodynamics, massive objects like planets and black holes create curvature in space-time, which dictates how objects move. However, extreme scenarios suggest that space-time could be warped or even engineered to allow for phenomena such as wormholes, warp drives, and artificial gravitational fields. Theoretical solutions like the Alcubierre warp drive propose using negative energy or exotic matter to compress space in front of a spacecraft and expand it behind, enabling faster-than-light travel without violating relativity. Similarly, traversable wormholes could act as cosmic shortcuts if the right space-time conditions exist. While geometrodynamics is grounded in general relativity, practical space-time engineering faces significant challenges. The main obstacle is the requirement for negative energy, or exotic matter, which has not been observed in sufficient quantities. However, quantum effects such as the Casimir effect hint at the possibility of negative energy in certain conditions, sparking ongoing research into whether spacetime manipulation could one day be achievable. Understanding geometrodynamics is crucial for advancing gravitational physics, quantum gravity, and future space technologies. If humanity ever masters spacetime engineering, it could lead to breakthroughs in faster-than-light travel, artificial gravity, and new ways to explore the cosmos, pushing the boundaries of what is physically possible. Level 95, Quantum Teleportation. Quantum teleportation is a phenomenon in which quantum information is instantaneously transferred between two distant locations without physically moving the particles themselves. Unlike science fiction teleportation, which involves transferring matter, quantum teleportation is limited to transmitting the state of a quantum system using the principles of entanglement and quantum measurement. The process relies on quantum entanglement, where two particles become so deeply correlated that measuring one instantly affects the state of the other, no matter how far apart they are. In quantum teleportation, a sender, Alice, and a receiver, Bob, share an entangled particle pair. Alice then performs a quantum measurement on an unknown quantum state and one of her entangled particles, collapsing its state. The results of this measurement are then sent through a classical communication channel to Bob, who uses this information to reconstruct the original quantum state on his entangled particle. While this process does not allow for faster-than-light communication, it is a crucial technique for quantum computing and quantum networks, enabling secure information transfer in quantum cryptography. Scientists have successfully demonstrated quantum teleportation over distances exceeding 1,200 kilometers, paving the way for a future quantum internet that could revolutionize global communication. Beyond information, researchers are now exploring whether quantum teleportation can be extended to energy transfer. Theoretical studies suggest that energy might be teleported across quantum systems under certain conditions, hinting at new ways to harness energy at microscopic scales. If this becomes feasible, it could lead to groundbreaking applications in quantum energy distribution and future space technologies. Quantum teleportation challenges our classical understanding of reality, reinforcing the idea that information and energy can be manipulated in ways that defy intuition. As research advances, it could reshape the future of computing, communication, and fundamental physics, unlocking capabilities beyond anything achievable with conventional technology. Level 96, Bekenstein bound. The Bekenstein bound is a fundamental limit on the amount of information that can be contained within a finite region of space, given its energy and size. Proposed by physicist Jacob Bekenstein in the 1970s, this principle suggests that there is a maximum amount of information that any physical system can store, linking entropy, information, and the nature of space-time in ways that challenge our understanding of the universe. The idea originated from black hole thermodynamics, where Bekenstein realized that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This means that the amount of information a system can contain is fundamentally limited by the area enclosing it, rather than the three-dimensional space inside. The Bekenstein bound sets an upper limit on how much information can be encoded in any physical system, reinforcing the idea that reality itself may be fundamentally digital at the deepest level. This concept has profound implications for quantum gravity, black hole physics, and the ultimate limits of computation. If information storage is bounded, it suggests that the universe itself may function like a holographic system, where the maximum possible information is encoded on a two-dimensional surface. This is closely related to the holographic principle and ADS-CFT correspondence, which propose that all of the physics inside a region of space can be described by a lower dimensional boundary. The Bekenstein bound also impacts the future of computing and data storage, as it defines the physical constraints on how much information can be packed into a given space. It challenges the notion of infinitely powerful computers, placing a hard limit on the amount of computation that can occur within a finite region of the universe. By setting a fundamental information limit, the Bekenstein bound hints at the deepest nature of reality, suggesting that space, time, and matter may ultimately emerge from quantum information itself. If true, understanding these limits could be the key to unlocking the mysteries of quantum gravity, black holes, and the fundamental structure of the universe. Level 97, Quantum Field Theory. Quantum field theory, QFT, is the fundamental framework that describes the behavior of all known particles and forces, except gravity, at the smallest scales. It merges quantum mechanics and special relativity, treating particles not as individual objects, but as excitations in underlying quantum fields that extend throughout space. This perspective revolutionized our understanding of reality, showing that everything is interconnected through dynamic energy fields. In quantum field theory, each fundamental force has an associated field. The electromagnetic field governs photons, the strong nuclear field binds quarks inside protons and neutrons, and the weak nuclear field governs radioactive decay. The Higgs field, responsible for giving particles mass, is another crucial component. These fields constantly fluctuate due to quantum uncertainty, meaning that even empty space is teeming with virtual particles that pop in and out of existence, a phenomenon observed in vacuum fluctuations and the Casimir effect. One of the greatest successes of QFT is the Standard Model, which unifies three of the four fundamental forces, electromagnetic, weak, and strong interactions, and correctly predicts the behavior of all known subatomic particles. Quantum electrodynamics describes interactions between light and matter with astonishing accuracy, while quantum chromodynamics explains how quarks and gluons interact to form protons and neutrons. However, QFT remains incomplete because it does not yet incorporate gravity, making the search for a quantum theory of gravity one of the greatest challenges in modern physics. QFT also introduces renormalization, a process that removes infinite quantities from calculations to make predictions finite and testable. This technique has allowed physicists to develop highly accurate models of particle interactions, leading to discoveries such as the Higgs boson at the Large Hadron Collider. Beyond particle physics, QFT has deep implications for cosmology, condensed matter physics, and even information theory. It plays a crucial role in understanding the early universe, black hole thermodynamics, and phase transitions in exotic states of matter. As research continues, QFT remains the best theoretical framework we have for describing reality, offering insights into the fundamental nature of space, time, and the forces governing the universe. Level 98, Emergent Spacetime Hypothesis. The emergent spacetime hypothesis challenges the traditional view of spacetime as a fundamental entity, proposing instead that space and time emerge from deeper quantum processes. In this framework, spacetime is not a pre-existing backdrop, but a secondary effect of underlying quantum information, entanglement, or other microscopic interactions. This idea is at the frontier of theoretical physics, attempting to bridge the gap between general relativity and quantum mechanics. One of the key motivations for emergent spacetime comes from quantum entanglement. Research suggests that the fabric of spacetime may be woven together by entanglement networks, meaning that the connectivity of quantum states determines the structure of space itself. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, links wormholes to quantum entanglement, hinting that spacetime's geometry might be a macroscopic manifestation of quantum correlations. Another major approach to emergent spacetime arises from holography, particularly the ADS-CFT correspondence. This duality suggests that gravity in a higher dimensional space is equivalent to a lower dimensional quantum field theory, meaning that what we perceive as spacetime curvature could actually be the result of quantum interactions on a distant boundary. This perspective aligns with the Bekenstein bound and holographic principle, which limit the amount of information that can be stored in a given region of space. Emergent spacetime also plays a role in loop quantum gravity and causal set theory, where spacetime is viewed as discrete rather than continuous. Some models suggest that at the smallest scales, spacetime behaves like a network of quantum interactions, and classical space and time only emerge when enough of these elements interact coherently. If spacetime is emergent, this could have profound implications for our understanding of black holes, singularities, and the early universe. It suggests that time itself may not be fundamental, but rather an approximation that emerges at macroscopic scales. If proven, this hypothesis could provide a pathway toward quantum gravity, explaining why space and time behave as they do, while unifying the laws of physics in a way never before achieved. Level 99, Limits of Physics. The Planck scale represents the smallest possible length, time, and energy scales where the known laws of physics break down. At this extreme limit, the effects of quantum mechanics and gravity become inseparable, requiring a theory of quantum gravity to fully describe reality. At the Planck length, spacetime itself is thought to lose its smooth, continuous nature and instead behave as a quantum structure, possibly made up of discrete units, or a fluctuating foam of quantum geometry. The concept of a spacetime foam, proposed by John Wheeler, suggests that at this scale, quantum fluctuations become so intense that spacetime behaves chaotically, constantly forming and dissolving tiny wormholes and bubbles. This extreme environment means that space and time may no longer exist in the way we understand them. The Planck time is the smallest meaningful unit of time, representing the instant after the Big Bang, when physics as we know it ceases to apply. Before this moment, quantum gravitational effects dominated, and theories like string theory, loop quantum gravity, and emergent spacetime models attempt to explain what happened at this scale. However, without direct experimental evidence, these ideas remain speculative. The Planck energy represents the energy at which gravitational and quantum effects become equally strong. If particles could be accelerated to this energy, far beyond the capabilities of the Large Hadron Collider, it might reveal new physics, such as evidence for extra dimensions, quantum black holes, or the fundamental structure of space-time itself. The Planck scale defines the ultimate frontier of physics, where concepts like locality, causality, and even the fabric of reality may need to be redefined. Understanding this limit is crucial for the development of quantum gravity, black hole physics, and the nature of singularities. If physicists can unlock the mysteries of the Planck scale, it could lead to the most profound breakthroughs in our understanding of the universe, from the origins of time to the true nature of space itself. Level 100, Mathematical Universe Hypothesis. This hypothesis, proposed by physicist Max Tegmark, suggests that the universe itself is a mathematical structure. Rather than mathematics simply describing reality, this idea posits that reality is mathematics, meaning that everything from fundamental particles to space-time and consciousness emerges from pure mathematical relationships. This hypothesis is based on the idea that mathematical structures exist independently of human thought, and our physical universe is just one of many possible mathematical structures. If the laws of physics can be fully described by mathematical equations, then it is possible that the universe is nothing more than a self-existing mathematical entity. In this view, all possible mathematical structures could correspond to physical realities, forming a vast multiverse of different mathematical universes. One of the strongest arguments for the mathematical universe hypothesis is the unreasonable effectiveness of mathematics in physics. From quantum mechanics to relativity, nature follows elegant mathematical patterns that seem to exist beyond mere human invention. Constants like pi, e, and the fine structure constant appear throughout physics, hinting that mathematics is not just a tool, but the fundamental framework of reality itself. If true, the implications of this hypothesis are profound. It suggests that consciousness, free will, and even the fabric of space and time are emergent properties of mathematical relationships. It also raises deep questions about the nature of existence. Does the universe exist because it is a valid mathematical structure? And if so, could all mathematically possible universes exist as well? While the mathematical universe hypothesis remains speculative, it provides a framework that connects physics, philosophy, and the search for a theory of everything. If the universe is indeed a mathematical structure, then discovering its ultimate equations may not just describe reality, but define what reality is, bringing us closer to understanding the deepest foundations of existence itself.